Cool. Wait, you know, I should. Oh, hey, Marty's here. Hello.
Hello.
Oh,
How you doing?
doing okay?
Yep.
Mm-hmm. Mm-hmm. Should move this off.
Yeah.
Matt, is that T-shirt generally available commercially?
I don't know anymore. I think it was from like a cupcake shop in New York.
Oh, okay. They're probably out of business.
It was like during the cupcake boom.
Magnolia.
You mean the nano cupcakes? Those,
Yeah.
is that what you mean?
It doesn't say. Yeah, related to that. I don't think it was Magnolia though.
Magnolia's out of business, aren't they?
Probably.
I think
I
so.
think they went under. Yeah.
I think it was called something like Two Hens.
They couldn't be out of business.
Two hens?
Something like that, yeah.
What about, okay, so repeat after me now that you said two hens. It's the Steve Allen memory test. Repeat exactly what I say. One hen.
One hen.
One hen, two ducks.
One hen, two ducks?
One hen, two ducks, three squawking geese.
One hen, two ducks, three squawking geese.
One hen, two ducks, three squawking geese, four Limerick oysters.
One hen, two ducks, three squawking geese, four Limerick oysters. And hard.
One hen, two ducks, three squawking geese, four Limerick oysters, five corpulent porpoises.
And a partridge in a pear tree.
No, corpulent part.
Steve Allen, my great-great-grandmother watched that show. Boy, Victor,
Wow.
you must be old.
I'm ancient.
Who was Steve Allen married
Well,
to?
it keeps going on and on. The idea is that they become more and more nonsensical. There's less and less relationship between that the idea that's coming and the idea that precedes it, and also there's more and more arbitrary elements in the actual individual parts of the text. So it becomes more. It's a more and more difficult test of your memory. It's like one hen, two ducks, three squawking geese, four Limerick oysters, five corpulent porpoises, six pairs of Don Alverzo's tweezers, 7,000 Macedonians in full battle array, eight brass monkeys from the ancient sacred crypts of Egypt, nine lyrical, spherical, diabolical denizens of the deep who hold forth around the corner of the quivy of the quay and sing all at the same time. Anyway, so most people die at around, even smart people die around 5.
Well, it seems like you really got to trust your muscle memory. Like the fact of having said it maybe makes it easier. Second time.
That works for trying to recite poems and passages from novels and so forth. Muscle memory. It's like sports.
Yeah. And the bike.
Steve Allen's wife died recently. Do you know who he was married to?
Who?
Jane Meadows. She lived to be 99, I think. She died recently. I read the obituaries. That's the first thing I read to see if my name or Victor's name is included.
Steve Allen wrote
You keep correcting
songs.
it every time.
Steve, somebody said he was going to say something about Steve Allen.
He wrote 1,000 songs. And there's several jazz songs that are very good.
Right, including his own theme song.
Yeah. This could be the start of something big.
Right. Who's Is that Jamie? Who said that?
No, Marty.
Oh, okay. I didn't see
Chaplin,
your lips moving, Marty. Are you a ventriloquist?
Chaplin wrote the music for all of his films.
Right.
That's right. What's it? Smile. His famous song is Smile.
And who was Steve Allen's famous sister-in-law?
Whoa.
Alice on the honeymoon.
Matthew Weiss probably doesn't even know who Steve Allen is, nor should you know, nor should you care.
But he probably heard of the Honeymooners, because a lot of people Matthew's age. Audrey Meadows was sister of Steve Allen's wife.
Oh.
Audrey Meadows was Alice on the Honeymooners.
Jane Meadows. Uh-huh.
Yeah, the young kids know about the Honeymooners. Is the funniest show ever on television.
Great. Yeah.
I've seen like one episode. Yeah, I'll go on YouTube later to educate myself. Well, that was very informative. Thank you very much.
By the way, Steve Allen discovered spin long before Howley, he wrote a song about it.
Probably.
So today, ultimately, I want to get to this quantum polyhedra stuff because it's fun to look at. First of all, but to get there, we got a bunch of things to get through. Not all of which we have to like dwell on. I will say though that last time I promised that we'd solve the prisoner's dilemma, and we never quite got to that. So I felt maybe we should start there, just in the interest of, keeping promises, and it was relevant to, the prisoner's dilemma is interesting because it's like at the heart of classical game theory and economics and stuff. And it's interesting to me that there's kind of a quantum loophole to it. So, okay, I'm sure most of you know about the prisoner's dilemma, but to refresh your memory, two prisoners are kept in separate jail cells, and the jailer's trying to get them to rat on each other. Each prisoner has to choose separately whether to cooperate, in this case meaning to stay silent and protect their fellow prisoner, or to defect, rat them out. In game theory, we always use the words cooperate and defect. If both prisoners cooperate and stay silent, then they'll serve just a year in jail. If, say, A defects and rats out B, but B stays silent, then A goes free and B will serve 5 years. And just the same if B defects and A stays silent. But if both prisoners betray each other, then each serves 3 years. So, it's obviously the best if both of them stay silent and cooperate with each other. It's sort of like, oh, okay, if both of them betray each other, they just stay in jail for 3 years. But individually, for each prisoner, it's the worst if they're trusting and they're like, oh yeah, well, I'm protecting my friend and their friend fucks them over, then that's the worst case. And because of that sort of incentive structure, a rational actor, as they say, will always betray their partner. Although the best situation is if both stay silent, they can't necessarily trust each other, and if they're betrayed, it's worse for them if they cooperate than if they betray. So you can imagine a quantum prisoner's dilemma, however. Well, I should say also, even in the classical case, this is meant to model, general coordination problems where people have to somehow trust each other to do the right thing, even though they're in separate circumstances. And, it's often studied in like, where you repeat the game, have multiple players and stuff. And, you can consider all those generalizations. One interesting generalization that various people have come up with over the years is the quantum prisoner's dilemma, where we imagine that even though the prisoners are in separate cells, they can nevertheless share some entanglement. And, there's like nice proofs about, what you can do with entanglement. But I think this one is kind of like one of the cooler ones because, the classical prisoner's dilemma lies at the heart of so much game theory, economics, evolutionary theory, and stuff. So there's like many ways to sort of formalize, how to quantize the quantum prisoner's dilemma. And I'm just following like one, paper that laid it out, I thought, in a nice way. So, here we have a payoff matrix. You can see, okay, so if this is sort of, more or less related to the little story told above. You could imagine the numbers being different. The point is, the relative payoffs. So, Alice and Bob both cooperate. They each get 3 points. This is Alice's points, Bob's points. If they both defect and betray each other, they only get 1 point each. If Alice cooperates but Bob defects, Bob gets 5 points, Alice gets none, and so forth. So we assign the meaning of cooperate and defect to the two basis states, let's say, in the z direction. So, spin up in the z direction means cooperate, spin down the z direction means defect. We start the game in the tensor product of cooperate, cooperate. Now, one of the things that people will do is say, they'll say like, all right, we're gonna like entangle these two qubits using this little operator here, which is basically e to the I times some factor at times the tensor product of Pauli x and Pauli x. So this is like one of many possible entangling gates. And the point is people like to use it because by adjusting that gamma factor there, they can, basically choose how much entanglement they want to start the game with, and then study the game in different circumstances. So that, if, naturally, if gamma is 0, then we just get back the classical prisoner's dilemma. There's like no entanglement, nothing interesting. Conversely, if gamma is pi over 2, we end up in this state here, which is a maximally entangled state with, between, say, Bob and Alice, both cooperating or both defecting. Then, so we start off with the qubits and some initial state. In this case, cooperate, cooperate, just sort of establishing the conventions. Then we entangle them, and we give a qubit to Alice and Bob each. And what they're allowed to do is, like, whereas in the classical prisoner's dilemma, they just sort of communicate a signal like, I want to cooperate or I want to defect. Here, what they're allowed to do is perform some arbitrary unitary operation on their respective qubit. So, whoa. So since it's a qubit, they can rotate it, basically. That's what they're allowed to do. So they can rotate their qubit, and then they like return their qubit, each give their qubit to the jailer or whatever. And the jailer applies the inverse of the entangling operation, and then you get the final state, which is, you can think about as being measured in the z basis, and like we're saying, up signifies cooperate and down signifies defect. Now, so for example, like instead of, applying the inverse of the entangling operation, you could just measure in that basis. For example, they do like kind of a joint measurement on the two. You could kind of play around with this, but this setup just sort of makes certain things sort of nice and clear. So this is sort of summary of it. They start in the initial cooperate cooperates state. We get this entangling operation. Alice and Bob each do a unitary, and then we do the inverse of that, and then we look at the final state. So we can think of the payoff functions, in other words.
What is the unitary operation?
The unitary operation for Alice and Bob each is like whatever they want. So they're free to rotate their qubit, do any unitary, 2x2 unitary that they want to do on their qubit. E hat here is an entangling operation that's sort of controlled by gamma. And just for our discussion, we're going to take gamma to be pi over 2. So that effectively just starts us off in this maximally entangled state. So the point is like you could, study the different strategies as you, sort of increase or decrease the entanglement from like no entanglement to like maximally entangled and so forth. So then, you can sort of calculate the payoff functions for Alice and Bob, like how much can they expect to win as expectation values, basically. So, just given the probabilities for the different outcomes, whether it's gonna be cooperate, defect, cooperate, defect, etc. You multiply those probabilities by the amount that, Alice in this case is gonna win, given those outcomes, which can be found in this little table here. So, okay, so here's like sort of the punchline, and then we'll see like a little, have a little simulation of it basically. So Alice and Bob's challenge is they're trying to like maximize their payoff by choosing some 2x2 unitary operator to, apply to their qubit. Now, in the case of what if they just choose the identity operator? That's going to correspond to classically cooperating, basically because we start out in the cooperate state to begin with. And the Pauli Y operator is going to correspond to classically defecting. So if they just stick to doing those two operators, nothing happens in the quantum case that's different from classical case. But here's the cool part. So, for example, if both players instead apply the Pauli Z operator, then, okay, first of all, the final state always equals cooperate. So, it seems like no different from just both of them applying the identity operator, or so you think. But let's call it Q, the magic quantum strategy. Inevitably, in all the literature, they do refer to it as like the magic strategy. In any case, what's magic about it? Okay, so if they both apply it, then it's just like both of them chose to cooperate. That's first of all. If, however, one of them applies the magic operator and one of them cooperates, then it's just as if both of them had defected, which is not so bad. If both defect, it's like it's only second worst, or it's rather second best. But here's the clincher, and this is the thing that really completely changes the incentive structure of the game. If Alice applies, say, the magic operator and Bob defects, then at the end, it looks like Bob had cooperated and Alice had defected. In other words, it flips it. And then therefore, instead of getting screwed over by their partner, they screw their partner over. And because of this, the rational strategy and the quantum prisoner's dilemma is Q in this case. And so basically by moving to the quantum case and allowing the two prisoners to share entanglement and creating this somewhat artificial setup, but of course, this is just mainly to get at the mathematical essence of it. You can imagine a lot of different instantiations of such a game. You can show that, a rational actor, far from defecting, in fact, is encouraged to, well, cooperate, basically. So here's a little simulation of the game. This function just basically does the whole thing, right? It's like, start off in cooperate state. Here's our entangling operator. This function takes two arguments, which are the two unitaries that Alice and Bob are both going to apply. Here's, we just apply, we start off in the cooperate state, apply the entangling gate, apply, the unitary on Bob's unitary, apply Alice's unitary, and then undo the entangling operation. We look at the probabilities. Here's the little multiply the payoff for each of the probabilities to get the expected payoff, and then we print it out. So let's do it. And then we look at it in a bunch of these cases. So, if Alice and Bob both cooperate, then they each get 3 points. Okay, that's just the same as the classical case. If Alice defects, betrays Bob, and Bob cooperates, then Bob gets screwed over. Alice gets 5 points. Bob gets 0 points. Sucks for him. Conversely, if Alice cooperates and Bob defects, it's Alice who gets screwed over. She's so trusting, it's terrible. And Alice and Bob both defect. They each get 1 point. So far, that's just the structure of the classical game. Then we throw in our magic operation here. We see that
there seems to be a little contradiction there. Go back up just a tiny bit.
Yeah.
You have okay. I'm sorry. Go ahead. I'm sorry.
When I was doing this, I often would be like, wait, which one is the one who gets the 5 points when they cooperate or when they defect? So, yeah. So if they both do the quantum operation, the magic operation, then it's the same payoffs as if they had both cooperated. If one of them does the quantum magic operation, one of them cooperates, then it's just as if both defected. It's like, all right. But then, here's the real cool part, right? Alice does Q and Bob does D. And, the comparable case is up here. It would be like Alice does C and Bob does D, which like Alice gets 0 and Bob gets 5. But here, when Alice does Q and Bob does D, then it's just the opposite. Alice gets 5 points. So in other words, by doing the magic quantum operation, Alice can protect herself against, Bob's betraying her, and Bob can make the same argument. And so, if you can do it, then the rational thing to do is both choose Q because, well, it's just as good as both cooperating. So, quantum prisoner's dilemma. You can imagine that being generalized and playing around with that in many ways. Any questions about that or comments or? I'll say,
is the purpose of it some sort of program design in quantum computing? Is that the purpose of the dilemma?
Well, yeah, I think that could be one application of it. Certainly if, game theory allows one to formalize a lot of different things, whether it's economics or even, the dynamics of concurrent programming and stuff. So I think that, if you're trying to, or even, I don't know, suppose the game was instantiated in some ways in some molecules or something like that, and you're trying to model, do some evolutionary dynamics kind of simulation.
Matt, is that a standalone lecture, or do we have to know that to understand what's coming?
No, that was just a little standalone. I just thought,
So we could Google quantum prisoner's dilemma if we didn't.
There's several references. There's in the bibliography, I list one of the ones that I used. And people talk about all sorts of generalizations of it, as I say, multiplayer. Imagine the players are in different locations in some space. I mean, I personally think it's interesting from the perspective of, and this is, my informed, uninformed, whatever, opinion or whatever, but a lot of, evolutionary theory as it was developed by Darwin, the whole theory of natural selection, et cetera, is a theory which in itself doesn't necessarily make assumptions about whether the world's classical or quantum, but the way that it's been applied is, basically under the assumption that the world is a classical place. And, therefore you can have a kind of like a rash of books, which I've seen, which all, take as their theme something like, well, since it's always rational, as we know, to betray and be selfish and be whatever, the thing that we have to explain is the evolution of altruism. How could it be that altruism, selflessness, whatever, cooperation could arise from, a bunch of faithless atoms bouncing around, et cetera? And, it's not, I'm sort of making fun of it, but like, I mean, that's a fair question, At the same time, though, it's not always clear that, the classical setting in which, due to the prisoner's dilemma, separated prisoners will always betray each other, is the appropriate setting. I mean, it's certainly true that, we have no idea to what extent quantum mechanics really matters to biology, from top to bottom. But when I think about the evolution of organisms from like the tiniest little quantum widgets to whatever in a cell and multiple cells and whatever, I mean, we're dealing with, the emergence of cooperation between, spatially separate entities and stuff. And, it seems to me, if you want to like think about the game theoretic analysis of how it was in like the interest or whatever of those little, microorganisms to cooperate or whatever, it wouldn't be crazy to think about, well, to what extent did they share entanglement? To what extent did that change, the risk calculus?
If you put it into evolution, the framework of evolution, and specifically human evolution, there's supposedly a limit of about 55 human beings in a human group, and once you move beyond that, you have far greater difficulties in cooperation, and then you require language systems that are more advanced that will then facilitate the cooperation. But if you now make the analogy between cooperation in a human group and entanglement in a social group, like a hunting and gathering group, the members of the group know they are entangled. And they know that the cooperation, they're in a face-to-face situation. They're not in separate cells like the prisoners. And so because of the presence of the other, the face of the other, which in 20th century philosophy is the basis for ethics, okay, in Levinas, you're going to have, you understand that you are entangled, and you understand thus that cooperation leads to the good of one and the good of all. So,
can I
Let me interject a little experiment that has been done with the prisoner's dilemma. People were invited to write computer programs that would play this game against each other. And the way it was run is the following. Every program was playing the game about 1,000 times against every other program. During the 1,000 times, it had a chance to learn about the other program, gain from this knowledge, and change its strategy accordingly. The final result was that the winning program was a very simple program. The program was the following. The first round, I cooperate. Every subsequent round, I do what the other program did to me. And this one won. So they published it. So everyone knew that this was the winning program, and people were invited to do the game all over again. So again, they wrote their programs and they played against each other. And at the very end, it is still the same program that won, even though everyone knew already that this is the program that won the previous round. So basically, the moral of the story is the following. The first time you meet someone you don't know, be friendly. Thereafter, do to them whatever they're doing to you.
Yeah, it's funny. It's like an empirical confirmation in some way of Kant's categorical imperative. I think they called it the tit for tat strategy. Yeah, my friend Jared.
In terms of the evolution of altruism, there are specific species, all mammalian species, that depend on for their survival on cooperation. Canines, felines, and primates. And so it's not, and this is not a quantum phenomenon. This is a macroscopic phenomenon. So,
sure. Yeah, I mean, I'm not like saying that all cooperation is quantum. It's just some cooperation could be.
But then there's also the study of self-organizing systems where quantum could come in.
There's, if you take the Prince of Machiavelli, right, and you have the possibility of the superposition of the lie and the truth, you know, and there's always the same irony at the opening of each of the passages in the Prince, and it says, one should always tell the truth. However, and so it's always the very, very same structure. So the program is written as in Moshe's case, you know.
Yeah, but Henry Kissinger, who is the chief advocate for Machiavelli in modern times, never told the truth. So,
well, I mean, he's being supremely ironic. He's saying one should always tell the truth, however, meaning one should never tell the truth.
Yeah,
that is what Machiavelli is saying. But of course, Machiavelli was a Florentine Republican, not an advisor to princes.
Back to spin.
Future. I wonder how popular Machiavelli's book was among the princes of his time, or if it later became more popular later. I don't know. So there's much more one could say about cooperation and game theory and evolution. And, you know, I think this story is really yet to fully be written. I mean, only when we have, you know, for 30, 40 years, you know, we've been running evolutionary game theory simulations on our classical computers. And, you know, like Moshe is saying, studying like what strategies arise when, you know, the population is composed of, you know, these kinds of agents who each do these kinds of strategies, and maybe they can switch strategy, or maybe they're playing on a graph, or maybe they're playing in all these different circumstances and stuff. And, you know, you study what kinds of things emerge. I mean, until we, I think, have, you know, the quantum computers at scale, we're not going to be able to do the same thing. And it'll be really interesting to see what kind of, when we can sort of model quantum agents who have the capacity to maintain, you know, entanglement and so forth, play different games, what kind of strategies emerge, what kinds of novel and unfamiliar forms of cooperation, you know, come up. I think that's something that we, you know, barely know how to talk about now, particularly as, you know, the methods that one uses to study quantum systems, I mean, are not necessarily amenable to that kind of, you know, like analysis, like we're doing with the, you know, like these kinds of simulations where, okay, play the game again and again and again, and so forth in these different circumstances. I mean, like a lot of the time, you know, excuse me one second. You know, studying, you know, something where the long-term dynamics and, you know, large-scale dynamics and the short-scale dynamics are kind of interlinked, you know, is obviously something that everyone wishes that they understood better. So, in any case, let us move on to talk a little bit about, okay, so we're trying to get to this quantum polyhedra business because it's cool and fits with our theme of talking about atoms. We're gonna eventually show that, you know, we're in the world of tensors. And one way of thinking about a tensor product that is confined to live in some subspace, in this case, the spin zero subspace, is as a vertex that conserves angular momentum. It's like a little site, a little theater of interaction for some spins. Spin's gonna come in and then like some spins are gonna pop out. The angular momentum that comes in has gotta be equal to the angular momentum that comes out. What's cool is that like that construction in the, you know, loop quantum gravity community is interpreted kind of convincingly as a quantum polyhedron, so that the site of interaction for spins turns out to be an atom of space. Is loop quantum gravity proven? No, but it's pretty cool that they can do this. So that's where we're gonna try to go. To get there, I mean, we got to talk a little bit about, you know, a couple things. So first thing to talk about is we all know and love by now the representation of a spin state as a polynomial. The roots of the polynomial turn out to be these points on the sphere that, you know, have to do with the probabilities. Okay. Well, there's like a related representation that in some ways is even more common to find, where we represent the spin state as a tensor product of 2J spin half states. So like, instead of it being like a polynomial with 2J roots, instead it's a permutation symmetric tensor product of 2J spin half particles. And it encodes the same thing. And indeed, if you like take your polynomial from before, find the roots, convert each root into a spinner, which you can do up to phase, and then take the permutation symmetric product of them, which just means take the tensor product of them in all possible orders, add them up, normalize it, then you get just this representation of the spin as a symmetrized tensor product of 2J spin half particles. And the map is reversible and it's 1-to-1. So like, let's see a little bit, like, first let's like motivate that a little bit. So suppose we had two spin half states, A, B, and C, D. You know, way back when we were like, okay, we could assign a homogeneous polynomial to them, you know, AZ minus BW and CZ minus DW. Well, we could combine them together. We could multiply them together. And that would just be, well, when you multiply polynomials, it's just combining their roots. You know, like you got a pile of roots, now we got a big pile of roots. So we get this homogeneous polynomial. AC z squared minus AD plus BC ZW plus BD W squared. Converting things into the standard JM representation, we get this state. Recall that we just look at the coefficients here and we run like our Majorana polynomial in reverse, you know, so we got this like -1 to the whatever term, and then instead of multiplying by the square root of the binomial coefficient, blah, 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 we divide by it. So, you know, refer to previous section for that. Susses out to this, AC times 1 over square root of 2, AD plus BC, BD. So you look at that and you're like, okay, well that makes sense. It's a spin 1 state, first of all. which makes sense because we started with 2 spin half states. We combine them in this way by like multiplying their polynomials. Therefore, this is polynomial with 2 roots, and therefore we get a 3-dimensional state, spin 1. So far, you know, that's basically what we've gone over before. But now let's consider, you know, compare that to doing the following. We take A, B, and C, D, and we take their permutation symmetric tensor product. In other words, we do AB tensor CD plus CD tensor AB, and we normalize it a bit. So if you work out the tensor product, you get this, and you add it up, and you get that. And you're looking at that, and what you know is that, you know, outside of the fact that, you know, okay, these 2 terms are the same here, you clearly have no more information, you know, in this permutation symmetric tensor product state than you do in the spin 1 state. In other words, it's basically the same components, okay? And that's, in a way, a heuristic proof, like that this is gonna work. The spin 1 state and the permutation symmetric tensor product of 2 spin half states basically encode the same information. More generally, we can look at, you know, suppose we have 2 spin half states.
One is Bohm and one is Copenhagen. Only joking. Only joking.
Okay. So suppose you had 2 spin halves. A basis for the permutation symmetric states of 2 spin halves can be written like this. It's 3-dimensional, and the 3 basis states are up, 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 down, plus down, up, and down, down. Each of those states, if you swap the 2 qubits, it literally doesn't change it at all. And like we've said above, this permutation symmetric subspace is 3-dimensional, just like a spin 1 state. Similarly, if you had 3 spin half guys tensored together, and you looked at the permutation symmetric states, there would be 4. Up, 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 and then basically here you see it's all the states where there's 2 up and 1 down added together, and then over here it's all the states where there's 2 down and 1 up. It's 4-dimensional, there's 4 of these guys, and that's just like a spin 3 half state. For 4 spin halves, you get this, you know, all the state, you know, 4 up and then 3 up, 1 down, 2 up, 2 down, 3 down, 1 up, and then all down. There's 5 of those, just like a spin 2 state. So, does this, okay. So this is some code. I don't know if this is that interesting, really. I just sort of a consistency check here. No, spin root's not defined. That's better. Okay, so what this does is it just sort of does 2 things. A, it calculates the basis states for the symmetrized tensor product like I did here. This just goes through all the possible, you know, 2 ups, 1 down, et cetera, et cetera, et cetera, bullshit. And it creates a matrix which, you know, implements this transformation. So it takes a, it takes a spin state, and if you multiply it by this matrix, it converts it to a permutation symmetric tensor product state. In other words, each of the components of the spin, instead of weighting, you know, the corresponding JM state, instead correspond to weighting one of these permutation symmetric tensor product states. In other words, if I had a spin, you know, 3 half particle, it would be 4-dimensional. I'd have 4, you know, components, and I would just multiply each of these basis states by those components and then add them up. And so we could instead, you know, do that with a matrix multiplication. And so this calculates that. So that's one way, right? That's one way to go from a spin state in the JM representation to a spin state in the permutation symmetric tensor product representation. It's a lot of syllables. The other way is what I said at the beginning, right? What we could do is take the spin, turn it into a polynomial, find its roots, convert each root into a spinner, and then take the permutation symmetric tensor product of all the spinners. In other words, tensor product of spinners in all possible orders and add them up. And my claim is that that will give you exactly the same thing. And indeed, the calculations bear me out. There it is. True, it says. Okay, well, it's true up to phase. In other words, it's true up to multiplying by any complex number. So if you really want to keep track of that phase, which you may want to, it's important, you should use this little matrix transformation. But if you don't care about the phase, you may as well just use this. So you see there's like an intimate relationship to this polynomial finding the roots shit and this permutation symmetric tensor product representation. But crucially, do not think that it's like I have a bunch of spinners that represent the roots of my polynomial. Let's say there's 3 of them. And then I, take their permutation symmetric tensor product, etc. And I end up with a state of 3 spin halves tensored together. Do not confuse those 3 guys as being like related to the individual stars or the individual roots. In fact,
the term you're using, spinner, is this from Penrose spin networks? Is that what it is? And you're trying to relate it later to loop quantum gravity? Is that what you're?
So a spinner is just like this, okay. You're dealing with a 2-dimensional complex vector. Now you could call it a spin half state. Okay. But that's sort of to emphasize, its use in describing spin. I mean, it could represent polarization too, for example, of some particle. In the context of quantum computation, you call it's a qubit. The relevant thing being it's like a 2-state system, whatever it represents. A spinner is just the same construction, but the norm is allowed to vary. In other words, it's not a quantum system necessarily, it's like a classical thing. So it's just, you could just say like a spinner is like an unnormalized qubit state. In other words, it specifies a direction, it specifies a phase, and it also, if it's unnormalized, can represent also some magnitude, which is constrained to be 1 in the case of the qubit, for example. So you can use the spinners for a lot of different things. And when we come to our polyhedra, yeah, we'll see a cool use of it. Penrose loves spinners. It's absolutely true. Sometimes sometimes people refer to what I just said as like the symmetrized spinner representation of spin, or the symmetrized spin half representation, etc. It's sort of semantics. Yeah, who came up with the term spinner? I don't necessarily recall, except to say that it may have been Cartan, even before the First World War. What's with that? Before anyone had any idea that they would be useful. Okay, here's a cool thing. You may have wondered, possibly, every time I've done a little computer simulation so far of these like higher spin particles, I'm always using like these higher dimensional Pauli matrices. In other words, for like a spin 1, say, there's like some 3x3 matrix that will like do an X, be the generator of X rotations or generator of Y rotations or generator of Z rotations. And there's such a representation for, spin half, spin one, spin three halves, whatever you like. In any dimension, there are, there's a representation of, XYZ generators. And I've just sort of taken that for granted in the sense that I have not explained how to calculate them. I've just used the fact that Q-tip gives them for you, There's just a function you call. You're like, give me the one for spin three halves. And it just gives it to you. But we can now see how to calculate it. Like, from first principles. Like, I mean, if you think back, like way, a couple of weeks ago, it was like, we were playing around with complex numbers and we like mapped the complex numbers to the sphere. And then we looked at like the 6 cardinal points on the sphere. 1, -1, I, -I, 0, and infinity. And then we associated each of those complex numbers to a spinner. And then we imagined that antipodal spinners were eigenstates of some operator. Eigenstates of the X operator, Y operator, and Z operator. And then we constructed the Pauli matrices by assuming that, X plus was associated with the eigenvalue 1, and X minus was associated with the eigenvalue -1, and similarly for Y and Z. And so we just like invented the Pauli matrices from like purely like conceptual geometrical, argument. So the question is, well, can we then like, continue on and be like, well, what about the representation of the Paulis for any spin? And it's a simple exercise now that we know about this symmetrized tensor product representation, because we know the spin half representation. They're just the normal Pauli representations. So for example, I can upgrade the normal, say, Pauli X to act on a spin 3/2 state in the symmetrized tensor product representation, just like this. It just is the sum of Pauli X on the first guy plus Pauli X on the second guy plus Pauli X on the third guy. In other words, you just do X to all of them. Similarly for Y, and Z, and like, in fact, whatever operator you want. But then, the cool part is, here we calculate this matrix transformation that can take us from the JM representation to the symmetrized tensor product representation back. Well, we can use that to transform matrices as well. So, we take this, this operator here, which is, the spin half version Pauli X acting on the first guy, second guy, third guy, added up. And we just, multiply it by our change in basis matrix, with the dagger on the left, thing on the right. And this will give us, in this case, the 4x4 matrix, which is the Pauli X for spin 3/2. So this is a little program that does it. This calculates our little matrix transformation. Here we, build up the X, Y, Z operators in the, acting on each of the symmetrized spinners. And then, each one, we like downgrade it to our JM representation. And we show that the X, Y, Z matrices that we get are identical to the ones that Q-tip gives us. Kind of like a proof, right? And, if you want, you can change the J value. So that's cool. Gotta love that. Okay. So, we played a lot with spin. We can represent a spin J state as a set of roots or XYZ points, a single variable polynomial, a homogeneous 2-variable polynomial, a JM state, and also a state of 2J symmetrized spin halves. In the latter case, we can swap any of the symmetrized qubits or whatever, and this doesn't change the constellation. In other words, this is like kind of, okay, so for this part of the talk or whatever, this is like the philosophical punchline. The constellation, which before, if you think about it, like if you have a polynomial, you got your roots. those roots are kind of encoded holistically in the coefficients of the polynomial. In other words, each coefficient depends on all the roots in some different way. You know, the same thing goes on here, but now, you know, this holism is of an even more dramatic sort in the sense that our constellation is encoded in the entanglement, specifically the entanglement between the qubits or the permutation symmetric spin half guys, not in any of the individual spin half particles. So for example, you know, suppose we like rotate just like one of the symmetrized qubits. You know, this is not going to lead to a rigid rotation of the whole sphere. That would be the case if we rotated all of them. In fact, if we just rotate one of them, we're no longer in a permutation symmetric state. But we know that a local rotation can't change the entanglement between the parts, right? It's just a local operation. So, you know, as we've seen, like what is the form of a generator of X rotations? Well, it's just X rotate each of the local qubits in turn. In other words, I can, if I just rotate one guy, oh shit, you know, I fucked up my constellation. I'm no longer in a permutation symmetric state. What do I do? Oh, well, if you just rotate everybody else in exactly the same way, then you restore the permutation symmetry. And indeed, this shows that in some sense, you know, no matter what local operations you do, as long as you do local operations, you can always recover that original constellation. In other words, the constellation is encoded in the entanglement specifically. And you know, this is cool because it's like, okay, so this is like a representation of spin, and it could be just used to represent, you know, the spin of a particle. But, you know, it could also be like, in fact, the state of a bunch of qubits. In other words, I could distribute the qubits off to like a bunch of different people, you know, one's in your quantum computer, one's in your quantum computer, and whatever. These individual parts could be scattered around the universe, but the constellation that is associated with them is still there, and it's encoded holistically in their entanglement and not in any of them individually. There's a connection, and people use this to study something called SLOC, stochastic local operations in classical communication. Basically, given some like multipartite state, you know, what states can you regard as being basically the same if you're allowed to do local rotations, if you're allowed to do like the local operation, which consists of like adjoining an auxiliary system, entangling them or in some way, and then measuring the auxiliary system, which then, you know, makes it go away. So that's like a form of local operation that doesn't change the entanglement relationship to anybody else. And then also supposing you're allowed to call up the people who have the other parts of the entanglement, the other pieces of the tensor product, and tell them stuff. So stochastic local operations in classical communication. And you want to sort of characterize states by, you know, characterize like a tensor product based on which states can be converted to each other under those operations. And so there's some interesting papers which you can find in the references that, you know, pose this question in terms of the constellations that we know and love. Interpretatively, again, you know, when we talked about the spin and the, you know, the stars or the points or whatever you want to call them, the roots, one thing we remarked, you know, on was like how classical it was. In other words, we could think about this like, okay, there's like a sphere, and then there's these like point particles confined to the surface of the sphere. We could like rewrite the Hamiltonian as like, you know, encoding these interactions, pairwise interactions, three-way interactions between these stars. And it seemed like, yeah, okay, so, you know, in some way or other, that's perhaps hard to imagine. Like, the spin really is just these particles on a sphere, and they're, you know, just considering an isolated spin, they're just evolving more or less classically, feeling forces generated by each other and so forth. And then, so this sort of question arose, even though there is this classical description, are we allowed to say that the spin really is just classical system? And, you know, I think once you start playing around with multiple systems and entanglement and so forth, you know, that view becomes untenable, and particularly dramatically here. Because as we've seen, we can represent exactly the same system as 2J entangled qubits, where the constellation is encoding the entanglement between the qubits. In other words, I could have a qubit over there, a qubit over there, a qubit over there. Like, indeed, if I could, you know, have a quantum computer and encode a spin J particle as like, you know, 2J qubits arranged in like a row, you know, in my quantum processor. And, you know, I could have them all evolving under some Hamiltonian, which is just the symmetrized version of the Hamiltonian that would have acted on just like the spin J particle. And the thing is, like, you wouldn't want to say that, you know, the constellation just was that classical system of these points on the sphere interacting, because there isn't even just one quantum system. It's actually like this qubit, this qubit, this qubit, this qubit. That constellation from before is encoded in the relationship or the entanglement, like between a bunch of quantum systems, not in any one quantum system alone. So, you know, there's that. That's kind of cool. Okay. So now we're like kind of sliding into the polyhedron stuff, but I'll pause if there's any questions about this symmetrized spinor picture of spin. You know, in I mentioned to Michael on comment for this meetup that it's worth checking out the first chapter of Rovelli's book, Covariant Loop Quantum Gravity, and, you know, this paper, Polyhedra and Loop Quantum Gravity. If you look at the bibliography, there's a bunch of other references too, many of which are great. But for example, you know, Rovelli employs the symmetrized spinor representation, or he alludes to it. It's very common. And if you know anything about, you know, Penrose's spin networks, you know, that's one of the relevant things that goes on there. You know, if you recall, you know, you sort of describe interaction vertices in terms of like threads, and they gotta like match up to whatever. And at the end of the day, this is related to this particular representation of spin. So, you know, check out the references. Because one thing you can say is that, you know, you can kind of think about it like having an extra symmetrized spin half there is like having like another quantum of angular momentum. And if you were then thinking about, like, suppose you had a spin one particle, it's got two spinners, and a spin 3/2 particle, it's got three spinners, and you want to know, you know, something about their total angular momentum, or like how do they interact, you know, you sort of pose the problem in a nice way if you work with the spinor representation, because each of the states is kind of broken down into these common building blocks, you know? And so, you know, you could make those like talk to each other. In fact, that's exactly what you do. So like, so, you know, if you had a spin one, you could imagine contracting those two. This is not the full answer, but this is just heuristically for the moment. Each of these represents a spinner, and like we could contract one spinner on each side, one spinner on each side. Now, the way I'm drawing this out should make you remember way back when, back when we were talking about wormholes all day, I was using string diagrams a lot, yanking and whatever, quantum teleportation, et cetera, all that bullshit. So back when we were talking about that, we defined the cup and the cap to be, say, oh shit, oh wait, right. Bing, 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 bing. The cup and the cap to be these states. In other words, the cup is just the up plus down state. And the cap is the adjoint of that, just the bra version. And that was cool for us. Now, if you recall, in one meetup, we were sort of talking about interpreting these string diagrams in terms of time reversal. In other words, when we thought about this as like teleportation, what was cool about it was like, particle comes in here, and it seems to like follow this like curvy path and like pop out here. But what was weird about that, right, is like this is from our perspective. And so if really the state does take this path along this wire, then we have to say like, oh, it goes forward in time and then slides across space, goes back in time, slides across space, and then starts going forward in time again. And we're like, what? So we talked about that for a bit. And in doing so, we sort of like talked a little bit about formalism for like thinking about that stuff. I won't go into the whole thing there. But one of the things we alluded to was that if you want to reverse time for a spin, in other words, turn a spin from a bra into a ket, you should flip its XYZ components. We just sort of mentioned this in passing. So this becomes the name of the game here. This is like what we're going to have to deal with. In other words, in spin world, and this is like the theory, gets at the theory of like, when you talk about how to calculate stuff with the spin networks, we use a different definition of the bra and the ket. Specifically, we use the famous Bohm state or whatever, the antisymmetric state, often called the epsilon. So the cup and the cap are going to be, are going to be the antisymmetric state. And indeed, that's what you do here. All right. So this, when I write this is, we're taking two spinners on either side and we're contracting them with the so-called epsilon. I don't know why they call it epsilon. But okay, so that's just a little summary of where we're going to go with it.
Question?
What's that?
Yeah, I hope I'm not going too far afield, but Matt, have you thought about how this might relate to Maldasena's ADS-CFT, where a spin-2 graviton, in 5 space could be contracted to a lower spin particle in 4 space? I was just curious if, there might be a relationship to ADS-CFT, which is the current rage.
Yeah. Well, yeah, I mean, look, I think there is, in some sense. But it kind of goes deeper than just ADS-CFT. Like, I just mean something like, talking about holography, there's a sort of a relationship between like a boundary and a bulk. And you know, things that are like highly localized in the bulk are like spread out on the boundary, and things that are localized on the boundary are kind of spread out in different ways. And there's like this sort of complementary relationship that people are always still trying to determine more of.
But of course, it's, you know, it's more specifically, it's about a graviton, a spin 2 particle in the bulk, equating to a lower spin particle
Right.
on the boundary in, you know, QFT.
I can't speak to that exactly, but I can say this much, that like when, you know, we're talking about, you know, say like the addition of angular momentum, or the addition of like any physical quantity, or in other words, you know, we have like the tensor product of, you know, multiple particles of the same type, and we want to know, you know, what can happen. We'll see that, you know, what I've sort of implied about this symmetrized spinor representation is we can view a JM state, you know, where the J can be whatever. And again, for different groups, I mean, this is like just applying like SU2. You know, this is going to be more complicated if you're dealing with SU3 or like other things. Here's a you know, a state, here's a state. Well, what I've said is something like, well, you can kind of split this stuff out into little atomic components, like in this case, the tensor product, the permutation symmetric product of 2 spin halves. Here, permutation symmetric product of 3 spin halves. In other words, you've taken these two things and you've kind of like re-expressed them in sort of these like atomic constituents. And the relationship between the constituents and the whole is kind of like holographic in a way. It's kind of holistic. And in terms of these, we can describe in a way how these things can couple together by, say, like contracting the atomic elements with each other using some appropriate cup or cap. And so I can't speak to, you know, as you say, these sort of correspondences and like ADS-CFT between, you know, different kinds of particles in the bulk versus the boundary. But as like a general, like very like high level kind of pattern, you know, I think that this sort of idea of taking something and breaking it down into atoms, which in some sense holistically combine to give it, and that is a sort of basis for a principle of interaction in general. That sort of makes sense. You know, like I think, I mean, in some ways, I mean, they're like toy models of holography. So for example, like, you know, I think the simplest one is like a certain error correcting code for 3 qubits. 3 Q-trits, 3 spin 1 particles, basically. So you have 3 Q-trits, and they each encode.
Well, it's a single Q-trit. It's three spins that are linked, but it's a Q-trit.
Exactly, yeah. So it's, yeah, what's hidden inside, what's in like the bulk is just a Q-trit. And then on the boundary live 3 Q-trits. And then the idea is you can act on any one of the boundary Q-trits without screwing up the guy hidden in the bulk. But you can mess with the guy in the interior if you know, can act on at least 2 boundaries.
I was just curious if Maldacena, you know, ever thought of this. Moshe met Maldacena, but they didn't discuss this.
So, well, I mean, you know, so I guess what I'm saying is like bulk boundary correspondences are more widespread than just the specific example of like ADS CFT. Here's a simple example of that. I mean,
didn't Moshe also meet Thomas Aquinas? I'm only kidding.
Wrong religion, Victor.
I'm
Go
only
back
kidding.
to sleep. He met Moses, which means Moshe in Hebrew.
But I like to think of even just this, the stellar or constellation representation of spin as being kind of a very simple form of holography in itself, in just the sense that you have the JM state, and then you have like this constellation, and like I'm saying, this is like, think about it like the coefficients of a polynomial. Each of these depends on like all the roots. Each component depends on all the roots. Each of the roots depends on all the components. So that, you could think about this as like being on like the boundary or whatever, in a heuristic kind of way. But yeah, I mean, totally. Like I keep sort of emphasizing this theme about like atoms and composites, and like to treat, this is now not a sphere with points on it. This is just now a pile of pebbles, right? Like to treat this as like the number 3 is to treat, these as like indistinguishable in some way. The fact that this is the number 3 stands in a kind of holistic relationship to each of these, kind of depends on the fact that there are all of them there, all 3. The act of gathering up atoms to form a composite out of them is...
This could be used to describe scattering processes where
exactly.
spins are changed.
Exactly, right. So, well, that's a good segue right there. So, basically, so suppose we have just 2 spin half particles. They're not symmetrized or anything, it's just any old 2. Now, normally we would describe that like in the standard basis, tensor product basis of up, down, up, and down, down. So we could write the states of the 2 particles as a linear combination of those guys. But there's another interesting basis that we could use. The basis of basically the total spin operator, total angular momentum, which is just basically the sum of all the x operators and all the spins plus sum of all the y operators, added up. So, the simplest way of just doing this is to just do it. Like, you know what I mean? Like, got 2 spin halves. X is the operator that acts. It's like X on the one guy, identity on the one guy, plus identity on the other guy, plus X on the other guy. And we take X squared plus Y squared plus Z squared. That's our J squared operator. We find its eigenstates, and we can, describe a state in that basis. Okay, but what's the point? If we look at what those states are, they're these 4. What's cool is, first of all, we know these latter 3, well, they're just our permutation symmetric states from before. And we're left with, at the top here, this little anti-symmetric state. In other words, we can see that the state of a spin half and another spin half, when expressed in this basis, the total angular momentum basis, can be seen as a superposition of a spin 0 or a spin 1. So you see how like this makes a lot more sense when you already know about the permutation symmetric tensor product representation of spin. In other words, just by looking at this, you're like, oh yeah, that's a spin 1 state. You see what I mean? And you're like, oh yeah, that's just a little, it's one dimensional, so it's got to be a spin 0 state. And so that's cool, right? So you got like a, you know, 4-dimensional state, tensor product of 2 spin halves. You can think about in the tensor product basis, this being like and, like a conjunction, like this particle and this particle coexisting, tensor product. To work in this basis is to think instead in terms of or. We have a spin 0 particle with a certain amplitude, or a spin 1 particle with a certain amplitude. So like we're saying, it's kind of like scattering. 2 spin halves come in, boom, and it's like with a certain probability a spin 0 could come out, with a certain probability a spin 1 could come out. You know. And you know, there's an interesting connection between, you notice there's a sort of 1-3 decomposition here. Spin 0, 1-dimensional, spin 1, 3-dimensional, and you can relate that to the 1 plus 3 structure of a Minkowski vector. But we won't do that here. So, so we say, so written it out here. Tensor product of Hilbert space spin half and spin half can be rearranged as a direct sum and versus or of a spin 0 and a spin 1. So, you can just play that game however you like. If it's easy for you to construct the angular momentum squared operator and diagonalize it, then, sky's the limit here. You don't need to use any fancy techniques. You can find out such nice facts as if you have a spin half and a spin 1, it's a spin half or a spin 3 halves. Or if you had a spin half and a spin 3 halves, that would turn into a spin half or a spin 2. So that's a nice little rule. In other words, if you have a spin j and you tensor it with a spin half, it can either turn into a spin j plus half or a spin j minus 1 half. If you have a spin 1 tensored with a spin 1, it can turn into a spin 0 or a spin 1 or a spin 2. And, sanity check, just think about the dimensions, right? Spin 1's 3 dimensions. Tensor product means like multiply the dimensions. 3 times 3 is 9. Direct sum is like add the dimensions. Spin 0 is 1-dimensional, spin 1 is 3-dimensional, spin 2 is 5-dimensional. 1 plus 3 plus 5 is 9, which is the same thing as 3 times 3. So we're good. Similarly, if you had spin 1 and a spin 2 tensored together, that's 3 times 5, turns into a spin 1 or spin 2 or spin 3. 3 plus 5 plus 7 is 15, same as 3 times 5, etc. And that should always work. If it doesn't work, you've done something wrong. One important case. So all these we've just dealt with like tensor producting, 2 spins together. But obviously you can iterate this construction to, handle however many spins you like. And one important case that is gonna come into play coming up when we finally get to the polyhedron is this case here. 4 spin half particles tensored together. You can kind of factor it out in different ways. And the ultimate conclusion is it's 2 spin 0 states, 3 spin 1 states, and 1 spin 2 state. And notice that there are 2 spin 0 states. In other words, the spin 0 subspace of the tensor product of 4 spin halves is 2-dimensional. And we will see that this is our quantum tetrahedron. Okay, we'll get there, we'll get there. A little foreshadowing here. Okay, so just a brief word on, using the symmetrized tensor product representation and our epsilon, our, fancy cup and cap to calculate this angular momentum decomposition. There's just a cool algorithm. It's worth mentioning because I'm saying it, it kind of gets at what I'm saying about, composites and atoms and stuff like that. So basically, you know, suppose you had two spins with spin J1, spin J2. Represent each one as a symmetrized tensor product of two J spinners. Okay. If you tensor them together and then symmetrize over all the spinners, we obtain a spin J1 plus J2 state. If the two spins we started with were not entangled, that would just be like taking their polynomials and multiplying together. In other words, combining the roots of the one with the roots of the other one, and just kind of overlaying them on top of each other. And we've seen if you take a spin half state and a spin half state, combine them together, you get a spin one state, where combining means just combine the roots. So in a way, we're going to be looking at that as, you know, you're getting your highest weight state. You could take two spins, form the symmetrized tensor product representation, tensor them, and then symmetrize over them. And then you get the highest weight state. So like I'm saying, in this case, it would be like spin half, blah, you get a spin one. But what about the lower weight states? What you can do is you got the one spin, you got the other spin, you break them down into your symmetrized tensor product. Imagine each of my fingers is like one of the symmetrized spinners. And the idea is before we symmetrize over them all, we contract K spinners of the first group with K spinners of the second group with the epsilon. And then we symmetrize, okay? So, you know, so you go through it. So first you take the two spins, symmetrize them, okay, you get the highest weight state. Then you take the two spins, contract two of the spinners, and then symmetrize. You get the next highest weight state. Then, you know, take the two states, contract two of the spinners together, and then get the da-da-da. Until finally say, well, if they had equal numbers of spinners, then you could contract them all and get, you know, an amplitude or a spin zero state. If they had different numbers, then, you know, you might get you know, a spin half state or something at the end of the process. And so actually doing this is just obtaining the so-called Clebsch-Gordon decomposition, or the, you know, decomposition of a tensor product into the direct sum of a bunch of spin states. And, you know, incidentally, it doesn't matter, like when you're going in there, you got your two symmetrized states, and you know, you're gonna wanna contract one with the other. It doesn't matter which one you choose, because after all, they're symmetrized. In other words, each is as good as any other one. So you just pick two random ones and contract over those indices, and it just works. So now there's like a sort of a complicated story involving like the normalization of these states, which we are going to ignore just for the sake of argument. But you know,
Matt, could you just summarize, you know, like in 25 words or less, how does this ensure conservation of angular momentum? And what's the gist of that?
Yeah, so basically it's like, think about each of the symmetrized spin half states as representing like a quantum of angular momentum. You know, so, you know, if you have two spin states, you combine them all together, it's just, you add up all the angular momentum. And so you get a spin J1 plus J2. And then in the other cases, you're considering like, well, what if we, you know, sort of removed a little bit of angular momentum from each one quantum of angular momentum from each side, and then symmetrized it. Now, the point of using, you know, the epsilon is like, you're basically, you know, sort of, I guess, like looking at the degree to which the overall spin's pointing in opposite directions. Is that true? Something like that. Yeah, so it's like a sort of way of like lowering the angular momentum on both sides.
So this ensures the conservation of spin angular momentum, but not total angular momentum.
Oh yes,
Okay.
we're only considering spin states. No position. No orbital angular momentum.
Can this be expanded to include orbital angular momentum, or is that a whole separate?
Yeah, no. Yes, I mean ultimately yes. There's going to be some like generalization of this construction in a way, for any symmetry group that you like. So this code, I mean, I don't even know if I bother running it in a way. Oh shit, there's a little error in it too. Well, all it does is just, Q-tip has a built-in Clebsch-Gordon calculator or whatever. So, you can use their built-in thing to like figure out what's this transformation from the tensor product basis to the angular momentum squared basis in a nice way. And so I calculate like the decomposition using that, the built-in thing, and then I do it, using the method that I just described, contracting each of the symmetrized spinders with the epsilon, k times or whatever, and show that you get basically the same result up to a normalization, which is just I didn't feel like dealing with. It's sad. Why does that not? Oh, sometimes. Well, let's leave that to the side. That's not an error in my code. I've just noticed this is like something that happens where I've got like two different versions of Q-tip. Okay, but here's the fun one. Oh no, I didn't want to do that. Sorry, I just got to move outside the Python notebook here for a second. Okay, because like, obviously we want to like see this stuff. So what we're gonna have here is, well, howdy doody. So it's been a while since I opened this up. I couldn't even remember what it was gonna look like. Okay, so, right. So what we got here is, above, you got these two blue guys. And the guy on the left is a spin 1 state, and the guy on the right is a spin 2 state. Now, what I've done is, in general, like they're going to be entangled. They're going to be density matrices. Now, how to visualize a density matrix, right? We can't just find the roots of the polynomial, blah, blah, blah. Instead, we can cheat, basically, and be like, all right, we have a density matrix. Maybe it's not in a pure state. Let's just find its eigenvectors. Each of those has a constellation. Each is associated with an eigenvalue. The eigenvalue will be the probability. And then we just display all of the constellations corresponding to all the eigenvectors, each with an opacity that depends on its probability.
How soon do you think you're going to be getting to the loop quantum gravity portion of the program?
Yeah, so that's coming up next. So I just, I want to motivate like how we, think about angular momentum conservation in this case.
We don't believe in quantum gravity.
Quantum gravity.
I'm going to leave just for a few minutes, but I just wanted to make sure that you knew all the news that was fit to print. This is for the physics group. This is from The Onion. Theoretical astrofetishists posit black holes could be used for anonymous sex across parallel universes. So,
Penrose already proposed
Penrose was in the
but Victor, if you leave now to take care of natural phenomena, you're going to miss the best part.
I'm coming back for the loop quantum gravity.
Well, just flush quickly.
So, all right, so what are we looking at here? What we're looking at is, so what I can choose is to combine two particles with different spin J values. So for example, in this case, I've chosen spin half and spin one. So on the left here, we see a little spin half state, and on the right, a little spin one state. Now, a spin half and a spin one can combine into either a spin half or a spin three halves. And that's what you see down here. So we have on the left a little spin half guy, and on the right a little, spin three halves guy. And like that's the Klebsch-Gordon decomposition. And the idea is that the opacity of the sphere has to do with the probability of it being a spin half or a, spin three halves. And like crucially, it's like, whereas at the top here, I have a spin half and a spin one tensored together, and they're evolving under some like, random thing. But, in general, they're going to be mixed states. And so as I say, I did this somewhat arbitrary way of visualizing a density matrix with the multiple constellations of the probabilities, which is misleading, of course, because, there are many such decompositions in a way of ways of writing a density matrix as a sum of weighted states and so forth, but, whatever. And so we see that, we get like these different constellations with different opacities up there, but that's not a problem when we're dealing with the decomposed states, where it's like a pure state of a spin half plus a pure state of a spin three halves, each with a certain amplitude. So, we could just do, how about a spin one tensored with a spin one? It should give us a spin zero, a spin one, and a spin two. So above we have our two spin one states in general and some mixed states. And then it decomposes into a little spin zero part, which, is just given by a complex number. So it's just a little arrow. And a spin one guy here, and a spin two guy with 4 stars. Again, each, whereas the two spin one guys are each in some like weird mixed state. When you decompose it into these sort of different sectors of different spin angular momentum, it's a direct sum of pure states, and the opacity is like the probability. So like if if we're thinking about it like scattering or whatever, it's like, imagine like two spin ones come in and like with a certain probability related to the opacity here, spin zero comes out, spin one comes out, spin two comes out, and so forth. Why not how about spin two and a spin, or how about spin three halves and a spin two or whatever. Look at that. What a lot of what a lot of stars. So this clearly decomposes into a spin half, a spin three halves, a spin whatever 5/2, and a spin 7/2. The saga continues. Does this make sense? Is this sort of, you see where I'm, the basic idea here? Maybe, one more thing we could do is, like, yeah, let's do this. Let's just look at like a more simple rotation or something. So like, let's do, Let's do like a, let's like look at like X rotations or something, you know? Boop, boop, boo, do, 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 do. Oh man, it's not really
Has the cameo by Carlo Rovelli begun?
nice. Hello.
No,
Oh.
not yet.
Victor, you forgot to flush. Carlo Rovelli is going to appear in a few minutes. He just gave me a call.
Okay, so one thing I want to emphasize is like, that's worth noting is, perhaps it's a little hard to see here, actually. Let me change it yet again to like this. Okay, yeah, nice. So that's easier to see here. Spin half combines with a spin 2. And I've initially chosen 2 separable states. Okay, so you got this constellation, this constellation. Now, this can combine into either a spin 3 halves or a spin 5/2. And look at the nature of this highest weight state. It's simply the combination of these 2 constellations. You look closely, this star, this star, this star, and this star are just exactly the same stars up here, plus this star. In other words, the highest weight state is just given by the conjunction of these 2 constellations. So I wanted to emphasize that. Yeah, it's not what I wanted to say.
I just want to let you know I'm only here for the animation. So
That's why I'm here.
I'm here to meet women. Where are they?
You let me know if you find some. Sorry, I should have set this up.
Michael, you are not here to meet women.
I'm not here to meet
I gave you the phone number of a lovely woman. You never called her, so you are not here to meet women.
Is she still available?
As far as I know, yes. I told you she lives in your neighborhood.
No, she lives on the west side. I never go to the west
No,
side.
she's on the Upper East Side.
She's on the east side. I thought she was on the west side. Well, if she's on the east side, I'll call her.
There you go.
Okay.
You're back. Okay, so this is the last thing I want to say about this, which is look at how this behaves under rotations. Okay, so we had a spin half state and a spin 2 state, and the Hamiltonian that I chose was simply a rotation on the spin half guy and a rotation on the spin 2 guy. And so we see, you know, if we just zoom in here, this guy's just rotating and this guy is just rotating. If we then look at their decomposition, each of those guys is just rotating in the same way. Okay, so I just make clear, you know, how this works.
Fermion is being affected by a graviton.
Yeah, if you want to, you know, interpret it physically, you know, it's an interesting point that, you know, you don't really see these higher spin particles as fundamental particles in nature. Why that would be involves some kind of complicated proof in quantum field theory that I don't fully understand. But okay. So now we know about like basically how to combine multiple spins into a tensor product, and can think about, you know, their, you know, angular momentum like decomposition or Clebsch-Gordan decomposition. So now we're really ready to talk about the polyhedron. So, you know, this is the punchline. We probably won't get through all of it today, perhaps, maybe, we'll see. Okay, so here's where I want to start with this. Like, again, just to preview where we're going. If you have a bunch of spin states, you can think about each of them as representing the face of a polyhedron, of a quantum polyhedron. If you constrain this tensor product to live in the angular momentum, or spin zero subspace. In other words, we saw for 4 spin half particles, the subspace of spin zero was 2-dimensional. So we have 2 dimensions of states that span this spin zero subspace. If you have that condition, then you can interpret this as a quantum polyhedron, and those 4 spins represent the 4 faces of a quantum tetrahedron. And the statement of angular momentum conservation, in other words, if we interpret these 4 spins living in the spin zero subspace as a vertex, an interaction vertex that conserves angular momentum, in other words, if we contract one particle with one of those states, it pushes out 3 states, say. The angular momentum of this incoming state is going to be equal to the total angular momentum of the 3 outgoing states. We can interpret this statement about the conservation of angular momentum geometrically to refer to the closure of the polyhedron. In other words, the fact that the faces all form a closed, convex shape in 3 dimensions. Okay, so that's where we're going. And you can generalize this to more than just tetrahedra, but in general, polyhedra. And this, okay, so like I'll begin with this observation, which is nice because it's sort of something that we're all familiar with. Like, we all know about unitary matrices, okay? Unitary matrix, multiply it by its conjugate transpose, which is its inverse, gives you the identity matrix. It preserves the norm of vectors, represents time evolution in quantum mechanics. We know and we love unitary matrices. Okay, well, here's maybe a thing about unitary matrices that you never ever considered before. I mean, at least when I learned this, I was like, damn, that's cool. I didn't know that. Okay, so if you look at its, say, the first 2 columns of a unitary matrix, first of all, they're going to be orthogonal complex vectors. Okay, perhaps you know that. That's not that surprising. So I just do it here. I generate a random unitary, look at its first 2 columns, and take the inner product, and behold, it's, okay, it's 0. Now consider this. You have a unitary matrix. You take the first 2 columns, they're orthogonal complex vectors, and you form spinors from pairs, like the first 2 components of each of those columns, the second 2 components. In other words, here's a unitary matrix. I just look at its first 2 columns, A, E, I, M, B, F, J, I, and then I form 4 spinors, A, B, E, F, I, J, M, N. These spinors, I call them spinors because they're not, necessarily normalized. So we can do it. We can look at them. Oh, look, they got norms all over the place, okay? Here's the cool thing. If you take those spinors, convert them into XYZ vectors, and add them up, then their sum will always be 0. So you take any unitary matrix you like, you look at its first 2 columns, you go along those 2 columns and interpret each of the 2 components side by side as a bunch of spinors. You take those spinors and you convert them into XYZ coordinates. How? The classic way. Just take the expectation value with Pauli X, Pauli Y, and Pauli Z. That gives you, n not necessarily unit vectors in 3 dimensions, add them up, it will always give you the 0 vector. So this relates to a theorem due to Minkowski. Yes, that Minkowski, about polyhedra, which is great. I mean, it's, it's nice to know, something that Minkowski did that like doesn't necessarily directly relate to relativity, although in a way this does. What Minkowski tells us, and I think this is from the 1890s maybe, he tells us that you can describe a polyhedron, sure, by specifying its vertices or whatever, but you can also uniquely specify a polyhedron by giving the unit normals to its faces and the areas of those faces. You have a polyhedron, you have a little vector that's like orthogonal to each of the faces, and you have the area of each face. If you multiply the unit normal of each face by its area, you get n vectors. Each vector points in the direction of the face, and the length of the vector has to do with the area of the face. If you add up those vectors, then you'll get the 0 vector. And that is just the condition that, in fact, the polyhedron is closed. It forms a legit polyhedron, like a convex shape. You could just imagine having like any old vectors, you add them up like this, the sum is not going to be 0. And so we can see that if we take a unitary matrix, look at its first 2 columns, they're orthogonal, complex vectors, pair off the components, look at them as spinors. We can interpret those spinors as representing a polyhedron, a closed polyhedron by Minkowski's theorem. So yeah, let's do it. Let's do it. Let's do it. Let's do it. Little anomaly here. Hold on.
Are you equally versed in Monty Python, or?
I was just watching some Monty Python the other day.
Have you seen The Tomb of the Unknown Joke?
Oh yeah. Yeah, that's like the very first episode.
The most brilliant by far, I think.
I was enjoying it, yeah.
Matt, I hope you can address this. I read the first chapter in Rovelli, as you suggested.
Mm-hmm.
And essentially, he's making an analogy between the normals to the polyhedral surfaces and angular momenta. So how do you just automatically make the analogy and say, well, what applies to the polyhedra surfaces also applies to angular momentum? If you can address that. See, this is where math and physics diverge. Although there are other ways to prove. I mean, obviously, Nether's theorem proves, well, at least classically, conservation of angular momentum.
Yeah. Sorry, slightly distracted by a. Oh God, sorry. I every once in a while I go back in and I try to like fix stuff up, make it better, and inevitably break some kind of dependency in the code. I'm sorry, I should have like really checked this over, before today. Okay, cool. There, nice. We're good. We're all good.
I'm sorry, did you hear my question?
I did. Yes.
Oh, okay. Okay.
He was reprogramming while listening to the question and imagining the very end of The Tomb of the Unknown Joke all at the same time.
All at the same time, yeah. That's the power. Yeah, why are we justified in interpreting, a tensor product in the angular momentum 0 subspace as a quantum polyhedron? which is to say, I mean, it sounds like you want to know something like, how is it that, demanding angular momentum conservation, like, is just this closure constraint on the polyhedron? Like, what's the simple, like, gut intuition about why that's true?
Can we use Nether's theorem to prove conservation of quantum angular momentum? I don't think so. Because
Well,
spin and orbital angular momentum are two different phenomena, but they are conserved. We know that.
right.
So I
So
don't know how you prove
Noether's
that.
theorem, basically says that if you have like a continuous symmetry, there's going to be some conservation law.
Right.
And yeah, so this is true. Now, like, we're not dealing with, like that sort of setup. Like, we're not saying like we have some field theory with some like Lagrangian and we're like looking at its symmetries and then like we're proving that some such quantity is conserved. We're working in this like much more discrete kind of context. In other words, I'm saying something like, if I
By
think
the way,
No,
just to answer
I
Michael's
know that
question, Michael,
quantum.
to answer your question,
Yeah.
yes, Noether's theorem definitely comes in. The symmetry group in this case is SU2. Invariance under SU2 gives conservation of spin by Noether's theorem.
Conservation of spin, but not conservation of total angular momentum, including orbital. But I have seen the proof where the sum of the spin and the orbital is conserved. I know that's been proven. But how do we analogize this thing about polyhedra that Ravelli illustrates
so if you think
to
about,
conservation of angular momentum?
if you think about it like, the closure constraint is like saying that like all these vectors have to ultimately be like pointing in opposite directions enough to like all cancel out to zero. And that's quite like an angular momentum constraint. In other words, you have a bunch of spins and you're like demanding that like their overall angular momentum all just like cancels out to zero.
Of course, representing angular momentum as a vector is a mathematical representation. Is it a physical?
Well, it
Is
turns
it
out to be
a real physical thing?
The idea is that in loop quantum gravity, at least, they claim that you can, sort of reinterpret the mathematics of spin to refer to like the faces of these polyhedra. In other words, the J value of the spin is basically the area of a face. And so,
Yeah, but that's an analogy. I mean, is that necessarily reality? I mean, we know.
Yeah, just the basis of their theory of quantum gravity, basically. And it's interesting. I mean, they didn't actually start from that. I mean, they started from this like other attempt to quantize gravity in terms of loops, in terms of like holonomies, and then we're led to to think about spin networks as like another way of thinking about these like loop spaces that they were like creating like back in like the early 90s. And then, the spin networks had been, Penrose had been thinking about those, years before. And, in a spin network, the idea is like at each vertex, you have some spins coming in, some spins coming out, and their, angular momentum is conserved. And that's like the whole point. It was then, subsequently that people started thinking like, hey, we could actually interpret the vertices of spin networks as being quantum polyhedra in a consistent way. So they were sort of like led to it through a circuitous route. I'm kind of telling the story in reverse in a way.
Because beyond itself, there
like,
becomes a question of the spin foam in loop quantum gravity.
Yeah, so the spin foam is, when you're considering like the dynamics of a spin network. You want to fix like an initial spin network, like a boundary spin network, and like a final spin network. And you kind of want to sum over all possible spin networks in the middle and get some, probability, like some transition amplitude. And yeah, like that's what a spin foam is going to be. I have to mention that there is a, oh, wait. I have to mention that there's a piece of code that I did not myself write. There's a guy, like a loop quantum gravity guy.
Did Jared Kushner write this code? I just saw a picture of him. By the way, we have to welcome Andre to the meetup.
Yeah, hey, Andre, yeah, just let him in. So it's kind of, so I've stated Minkowski's theorem, which is that if, you give me a bunch of vectors and I sum them and they sum to the zero vector, then I can interpret them as like the unit normals to the faces of a polyhedron multiplied by the areas of those faces. Now, question is, if I give you those vectors, like, how do you reconstruct like the polyhedron that they refer to? In other words, what are the vertices? Like, I want to draw it on the screen. And like that becomes, it's like kind of annoying, like let's just say. And so I am relying on this code written by this guy, Giuseppe Celaroli or whatever, who very kindly, I read his paper. He's like a loop quantum gravity guy. He's written papers in the field. A couple of years ago, I like noticed that he'd written a paper about like reconstructing these polyhedra from face normals and areas. And he was like, and this paper was like, and I put the Python code on the GitHub. And I went over to the GitHub and behold, there was no Python code. So I emailed him and I was like, dude, I'd love to have your code because I was trying to implement it and it was like not working. It's just like tedious basically. So anyway, thanks to Giuseppe over here, we got this. So he's got this cool code, polyhedric or whatever. So just thought I'd give a shout out to him. I think his name's Giuseppe. Good God. Hope I haven't misnamed him. Wait, let me just double check. I'm just, I owe so much to him. I couldn't do any of these. Oh yeah, it is Giuseppe. Okay, there we go. This is his paper, an algorithm to reconstruct
Giancarlo
from their face normals. Yeah, a lot of Italians in this loop quantum gravity world, I can attest.
Well, Rovelli is chief proponent of QCG. Yeah.
I don't know if it's because of Rovelli or what, but yeah, a lot of Italians, a lot of Europeans, generally speaking, actually. Okay, so what did I do here? What I did was I generated a unitary matrix. I, got these spinners out of the first two columns of it. I interpreted those as XYZ vectors, being, the normals weighted by the areas of a polyhedron. And then I called this polyhedric code to reconstruct the polyhedron, and then I visualized it. And I got this little polyhedron here. We could run it again and get a different, areas should be positive. Okay, well, ignore that. Get a different polyhedron. Okay, nice. Polyhedra are cool. So one thing that this implies is that there's an action of like UN on the polyhedra. In other words, I have like a unitary matrix that corresponds, I can like get a polyhedron out of it, but I could just like choose another unitary matrix to like evolve that guy, and that would evolve the polyhedron. So, not only do we just get, so look, now we have like a polyhedron, again, a classical polyhedron evolving in time. And this evolution will conserve the total area. Okay? So, it's interesting it's giving me that little error message there. So again, we've chosen a random unitary. It corresponds to a polyhedron. Then we choose, say, like a random, another random unitary, that's like tiny, and evolve the polyhedron under it. And the area at the beginning and the area at the end are the same. So we'll do it again just for fun because it's kind of cool to watch. It's a little slow. Let's speed it up. Let's go crazy.
But Matt, how does this relate to angular momentum? Yeah, the areas geometrically are the same.
So
but...
we haven't gotten there yet. I'm just talking about classical polyhedron. Sorry. Yeah, sometimes it has problems. Okay. Yeah, that's cool. That's cool looking. Look at that. Whoa, whoa, whoa. So yeah, this is just, yeah, look, it's kind of cool, when the vertices kind of like get near each other, there's all this sort of weird dynamics going on. So my point is like we're exploring the phase space of classical polyhedron. And then we're going to quantize it, basically, okay? So, but just we're trying to get a sense of like, how can we define polyhedra? How do we know, what's the deal with a polyhedron? And, the relevant thing is it's useful to think about the polyhedron, like not in terms really of its vertices, but in terms of the unit normals and areas of its faces. This is encouraged by Minkowski's theorem. And it turns out to be kind of like the right way of describing polyhedra when it comes time to quantize them. So there's that. Now here's a cool fact that I mentioned because it's cool. And also, if you want to read more about this stuff, I would say, many of the papers by this guy, Ettore Levine, are like really excellent on this subject.
Who is that?
This guy, Ettore Levine. I don't know if I'm pronouncing his name right, but...
Ettore, like Majorana?
Ettore. Hector.
What's the last name? Could you spell it?
Yeah, this guy.
Oh, Ettore.
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 Levine.
Levine? He's Jewish?
Levine.
Could be. He's got, going back a couple of years, he's got some great papers on a lot of stuff. So, okay, so here's a cool thing. Suppose we had like any random set of vectors in 3D. They don't necessarily satisfy the closure constraint. It turns out we can easily calculate a Lorentz boost, which acts on the spinors associated with those vectors and closes the polyhedron. In other words, we have just some random vectors. We can like always close them into a polyhedron by applying a particular Lorentz boost. If you think about it, maybe that makes sense, kind of try to imagine it in your head or whatever, It sort of surprised me when I was like, oh, is that really true? Well, it turns out it is. So here's a simple way of calculating it. You convert your vectors, again, not necessarily closed, into a bunch of spinors, and you form the projector for each one, in other words, the outer product, and you sum them all up. Then you do the singular value decomposition on that matrix, splitting it into some U times D times V, where U and V are unitary and D is a diagonal matrix. Then the boost that you want is the determinant of D to the -1/4 power times U times square root of D. And actually the boost you want is the inverse of that. This will give you a SL2C matrix. And if you apply that matrix to each spinor, it's gonna close the polyhedron. So, I generate here, just to check it, bunch of random spinors, okay? I can close them. You see I add up the spinners, do the singular value decomposition, just, you know, plug in that formula, and apply that little SL2C guide to each of the spinners. And I check the closure before I do it and after I do it, and you see I get, you know, these are all 0, so it is closed. Finally, it's worth noting, like, if we just had a set of spinners instead of a unitary matrix, we could act directly on those spinners. In other words, if we had a set of spinners and a unitary matrix that we wanted to evolve this polyhedron with, we could just, you know, take this sum. In other words, just go over the, you know, for each row, look at the components of the unitary, multiply them by each of the spinners in turn, add it up, do the same for each row, you know, again and again and again. And it ends up being the same thing as before. Okay, so that's kind of. All right, so that's classical polyhedra. What we've learned is that when we talk about polyhedra, you know, really the best language is provided by Minkowski's theorem. We want to think about, you know, the normals to the faces and the areas of the faces. So we can describe the polyhedron as a set of vectors. Each is a unit normal multiplied by an area, and the, you know, closure constraint, or the fact that, like, this is in fact a polyhedron, is just that the sum of those vectors is 0. Furthermore, we can explore the phase space, so to speak, of possible polyhedra of the same total area, in terms of, you know, the action of unitary matrices in n dimensions, where n is the number of faces. So again, this is sort of like classical, but you see, you know, like, it's almost always the case when you're working with, like, spinner world. It's like already we're using a lot of, like, quantum mathematics. We got spinners, you know, we got unitary matrices, right? It's like we're already practically there. But again, we're just describing classical polyhedra. Okay. So in terms of the quantum case, we quantize each face spinner as a spin J particle. In other words, when we do this quantization, and we'll see an example of where we, like, loosen this constraint later on. When we do this kind of quantization, the area of the individual faces of our polyhedron will be fixed. In other words, it will just be the J value, and it's not going to change. So if we had, you know, a tetrahedron, you know, the area of each face would always be like a half. And the evolution is going to preserve that fact, that not just is the overall area preserved, but actually the area of each of the faces is conserved. And there's a way of, you know, describing the phase space of classical polyhedra where the area of each individual face is conserved, but it's kind of a little more complicated, so I'm not going to talk about it.
Yes? Go for it. Sorry.
No.
And what? I can't hear what you're saying. Oh, okay. Well, I'm in a group here.
Okay.
Everything okay?
Yeah. It's my roommate who was coming in and trying to talk to me. Sorry.
No.
And then I figured out that all I have to do is cover the microphone. Sorry. Sorry.
So what we're going to do is, like, suppose we have a classical tetrahedron where it can be represented with these, like, 4 spinners representing the normals multiplied by the areas. And we're going to quantize each of these spinners as a spin J particle. So we have to choose, you know, the J value. We then consider the total angular momentum operator on each face is just going to be now the area operator. And the J values are going to be its eigenvalues. We can then consider the tensor product of, say, 4 spin half particles or n spin J particles representing the n faces, and form the total spin operator and demand that our state live in the spin 0 subspace. And as I've been saying, this is equivalent to the closure constraint. So, here's the case we considered before. The spin 0 subspace of 4 spin half particles is like 2-dimensional. And so we're just going to be working in that little eigenspace there. Okay. Now, from what I just said, though, you might think that, how do you recover the polyhedron in this quantum case, right? You might think like, oh, well, maybe it's like the expectation value of like XYZ operator on each of the face spins that gives you the unit, the normal vector to it or something. It's not how it works, actually. So instead, what we do is we define like all of the inner product operators between, say, the 4 spins, if we're working with a tetrahedron. So here's like a matrix of operators. I have XYZ operators that act on each spin, and I go through, all of the faces, and I take the X operator on the ith face times the X operator on the jth face plus the Y operator on the ith face plus times the Y operator on the jth face, and so forth. In other words, this is like a quantization of the inner product between the faces, or the normals of the faces. So you get this like matrix of quantum operators, which are like the quantizations of like all the inner products between the vectors. Along the diagonal, we have like the area operators, and the off-diagonal terms in some way should relate to the angles between the faces, because as we know, the inner product is like, the length of the one times the length of the other times the cosine of the angle between them. So in some way, this operator should be, related to the cosine of the angle or the angle, like whatever. If we have some polyhedron state, we can take its expectation value with each of the operators in this matrix and get a matrix of expectation values. We can then use the singular value decomposition, splitting G into U, D, V, where U and V are unitary and D is a diagonal matrix. We can consider the first 3, now this is like, okay, this is not obvious. We can consider the first 3 rows of V, flip them into columns, and make a matrix V prime. We can also consider the first 3 rows / columns of the square root of D and form a little guy, D prime. We then form the matrix V prime times D prime. It's not obvious, but the rows of this matrix will be the X, Y, Z coordinates of the face vectors. And the quantum closure constraint guarantees that these vectors all sum to 0. Now, here's the thing though. What I just said, that little weird algorithm, has nothing to do with the quantum part. In other words, we can show that it works in the classical case. So for example, what we do here is we generate a random unitary matrix. So basically a random classical polyhedron. We form the face spinners for it. And we convert those into vectors, XYZ vectors. Okay, so that's what this does. Then we form this matrix of inner products, sometimes called the Gramian matrix. So it's just the inner product of each of the vectors in turn. So if there's 4 vectors, it's going to be a 4x4 matrix. From that inner product matrix, or Gramian matrix, we can like undo what we just did. In other words, we can take that matrix, do the singular value decomposition, look at the first 3 rows, blibbity blibbity blib, and get the XYZ coordinates back. And so what I do here is, okay, I generate a polyhedron, get its vectors, and then create G, the inner product matrix. Then I can recover the vectors from G. And then from those recovered vectors, I find G2, which is the inner product matrix. And then you see that they're the same. Now, why did I do it that way? Because when you recover the vectors, you will recover the vectors up to a 3D rotation, okay? So you're not, when you do this singular value decomposition shit, you're not gonna get exactly the same vectors back in general. You're gonna get, you know, basically the right vectors for that polyhedron, but the polyhedron itself is not oriented in 3D, right? Like I can rotate the whole polyhedron and like it's still the same polyhedron. So this is important. The polyhedron is only defined up to an overall 3D rotation. So, you know, if we were to like look at here, just, you know, the vectors and then the recovered vectors, they would not in general be the same, but actually they do correspond to the same polyhedron. It's just one is rotated relative to the other. And we can see that when we form the Gramian matrix of both sets of vectors, it is the same, because this guy does not depend on the overall 3D rotation. So, okay. So that's just like a thing. You know, how to recover the face vectors from this matrix of inner products. You see it works in the classical case, and it will work in the quantum case, where, as I say, instead of just instead of having like a bunch of face spinners and converting them into vectors and finding this inner product matrix, instead we have this, you know, quantum state representing the polyhedron, and each component of this Gramian or inner product matrix is itself a quantum operator, and we can take its expectation value. And so instead of being just, you know, the literal inner products between the face vectors, the Gramian matrix will be a matrix of expectation values. And we can then do the same little trick with the singular value decomposition and recover the face normals or the face vectors. And we always find that they sum to 0. In other words, the expectation values of the inner product operators on our quantum polyhedron always, you know, basically correspond to it, like, in fact, being a closed polyhedron. And so, you know, so yeah, there you go. That's the basics of the theory. So let's like check it out. Got a cool viz going on over here. Beep, beep, beep. Examples. Which one do I want? Quantum polyhedron. Oh, here it is. Oh. All right, what is this even gonna be doing? Well, howdy doody. Look at that. Okay, so what do we got here? We have a tetrahedron. As I say, the state of a quantum tetrahedron is two-dimensional because there's the spin 0 subspace of the tensor product of 4 spin hat particles is two-dimensional. As such, it can be represented by a qubit. So on the left here, you have the tetrahedron, which has been reconstructed from the expectation values of all those inner product operators. And on the right, you have a qubit state, which is just the state of the, the two-dimensional state of the spin zero subspace. So, one cool thing is like, we can just easily like evolve this in such a way that preserves the angular momentum constraint by just evolving the qubit and watching how the tetrahedron evolves. So it's evolving ever so slowly there. And every once in a while, it'll flip and shit, like in a weird way. And that's because, this thing is defined only up to 3D rotation. And sometimes, as you're doing it, it's like the code that reconstructs the polyhedron decides, oh, I feel like using some other orientation. But you can see here, we're evolving this qubit, little two-dimensional quantum system, and the quantum polyhedron, it's gonna flux in correspondence there. So again, what goes on is in this code is I choose 4 J values for the faces. In this case, half, 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 and half. I diagonalize it. I diagonalize the total, angular momentum, spin angular momentum operator. And I just look at the spin zero subspace. And I'm like, it's 2-dimensional. And I form like this little qubit to just keep track of what my state is like in this little subspace. I then construct all these inner product operators because I got, X, Y, Z operators that act on each of the individual spins. I construct this matrix of inner product operators, and I can, given a state, which initially is just randomly chosen, I can form this matrix of expectation values. From that, recover the face vectors, send it over to polyhedric. It reconstructs the classical polyhedron, and then we visualize it. Now, here's the thing though. You might rightly ask, well, I mean, like, what's quantum about this, right? Like, you still got a polyhedron right here. I'm looking at it, right? Like, how is that how is that a quantum polyhedron? It looks like a classical polyhedron, right? It's like the same thing that we dealt with in terms of spin, right? Like, I have a spin pointed in the X direction. And, I measure it in the Z direction. And like half the time it's up in the Z direction, half the time it's down in the Z direction, right? And each of those states, like I could describe as just, well, it's just, just pointed up or it's pointed down. In other words, each of those states is like, at least for a spin half, like that's just like a classical state of a spinning particle. But from the perspective of like the X direction, to be pointed up is to be in a superposition of X plus and X minus. In other words, if I was to go measure in the X direction, I would get a random answer as a result. Okay. In other words, in the spin half case, I can always describe, the state like in a very classical way as just a point on a sphere given by the expectation values of X, Y, Z. But when I go to measure, right, I collapse into an eigenstate. And if I'm in an X eigenstate, say, then there's uncertainty with respect to Y and Z. In other words, if I measure X and I collapse to an X eigenstate, and then I measure X again and X again and X, I always get the same state. But if I measure in X and then I measure in Y or Z, I'm gonna get an answer at random. But despite that, I can always picture to myself the spin as just being, you know, pointed in a certain direction given by the expectation values. The exact same thing is happening here with the polyhedron. So what makes the polyhedron quantum is that the inner product operators, in other words, the angle operators, don't all commute. So you could say it's impossible to know the angles between all the faces in a quantum polyhedron at the same time. In other words, if I measure the angle between two of the faces, right, I get an answer at random. And if I measure that same operator again and again and again, I always get the same answer. But because I'm in an eigenstate of that angle operator, I can't be in the eigenstate of, say, another operator, which measures the angle between the faces. In other words, if I go to measure first this angle, and I get an answer, and then that angle, I'm going to get something random. There's quantum fuzziness. In other words, I can't measure an angle and then say like measure all the angles and then measure all the angles again and get the same result. If I collapse one of the angles to an eigenstate of this angle operator, then necessarily there's quantum uncertainty about the angles between one of the other faces, for example. But even so, the expectation values form a classical polyhedron. In just the same way as the spin, right? Like I measure in the x direction and it's like, oh, now there's quantum uncertainty if I measure in the z direction. But, you know, whatever. The expectation value just shows me that I'm just pointed in this direction. In the same way, it's like I have this like quantum polyhedron. It's like I measure it to be in an eigenstate of one of its angle operators. And then it's like, oh, if I go measure in like, measure one of these other angle operators, I'm going to get something at random. Nevertheless, if I look at the expectation values and form the inner product matrix or Gramian out of all of them, do the thing, I will get a classical polyhedron built out of these statistical averages. So for example, you know, with this little thing here that I've written out, it's like you can change the number of faces, the spins that live on the faces, you can evolve it and you can measure it. So for example, let us measure this spin. Let's measure the angle between the 0th and the first face. Now, oh, we got a degenerate polyhedron. Okay. This does.
Degenerate.
It's degenerate. Look, it's just like it's just flat. You see?
It's like a painting by George Groves.
Yeah, totally. So like this happens sometimes, and our polyhedron reconstruction code, thanks to Giuseppe, doesn't like it when, you know, you get these degenerate polyhedra. Okay, whatever. So I just show the face normals. But you know, okay, so now I measure the inner product between the first face and the second face. And you see, look, like we're in an eigenstate of this angle operator. And yeah, it's just a classical polyhedron or whatever. Let us I wanted to show here. Yeah, okay, nice. Just a quick little demonstration about what I was just saying about like the way that these things don't commute. Yeah, nice. So, okay. What this does is we generate a random quantum polyhedron, specifically a tetrahedron. Then we look at the inner product operators between the 0th and first faces, and then the inner product operator between the first and second face, okay? Now, both of these operators have eigenvalues negative fucking 3/4 and positive 1/4. Okay. Now, incidentally, when you actually, use this stuff for more or less like practical purposes in loop quantum gravity, there's like various conventions about, like exactly what these eigenvalues should be and so forth, but whatever, ignore that here. So those are the possible eigenvalues. Now, we have our randomly generated polyhedron, and we look at its inner product matrix, the matrix of the expectation values of each of the inner product operators for that polyhedron. And it looks like this. Cool. Then we measure the angle between the 0th and the first face, okay? And we see that we got eigenvalue negative 3/4. So this, and then we look at the inner product matrix after we've measured it. So you see what happens here is, here's the, the 0, this is like the expectation value of the inner product operator between the 0 and the first face. Indeed, it has collapsed to negative 3/4, as has this one, right? It's like symmetrical. Similarly, this angle, right, has it's collapsed to the same eigenvalue. This is the angle between the, 0, 1, 2, the second and the third face or whatever. But look at these. These have collapsed to 0. 0 is not an eigenvalue of any of these operators. In other words, at the cost of collapsing the angle, between these faces, this has led to intrinsic, quantum uncertainty between, the angle, regarding the angle between this face and this face. And yet, right? That is just another polyhedron. You know what I mean? You like, there, I just did it. It's like, I had a polyhedron, let's like, when you look at it, I measure the angle between, those two faces, and it collapses. But that itself gives you just another classical polyhedron formed from the expectation values, okay? So,
Where's Carlo?
where's Carlo? Great question. Let's do this. I'm gonna turn this off. Because the tetrahedron, how much
Matthew,
you hear about tetrahedron? Let's
Matthew,
do a fancy one. Yeah.
is there anything to be learned by the generalization of this to cases where the total angular momentum is not 0?
Yeah, so they look at that. Look at this guy go. So, yeah, some of the papers discuss this. I don't know. I don't know what to say necessarily, right? I mean, one thing I think about is like earlier I mentioned in the classical case, you can always like boost a set of spinners in order to close them. And then you think, what's the analogous thing to do in the quantum case? You have just like any old tensor product and, some kind of boost or whatever kind of forces it, pushes it all, like shunts it all to live in whatever is the spin 0 subspace or something. Is that a physical thing or whatever? I don't know. I'm not sure. I mean, one of the things they discuss in these papers is sort of like the the generalization of this stuff to sort of like polyhedra who like their face normals, you know, or like more like live in Minkowski space. You know, they're like space-like vectors. There's all sorts of generalizations. But certainly, like, what do I want to say? Like, I don't know. I think that's an area of I don't know. I'm not sure. I'm not sure what the full answer is. So look at this guy. That's, I don't know. I enjoy this. I think because it's like, you know, it's like, you know, you're trying to do some shit with 3D graphics, right? And it's like, what are like the most basic possible things that you could visualize? You know, it's like a sphere, constellation, and then pretty much after that, it's like, okay, a polyhedron. So, you know, here we go. Again, yeah, the areas of each of these faces is conserved. Each should be 1/2. So again, what we're dealing with here is I have 1, 2, 3, 4, 5, 6 spin halves tensored together. Yeah, what's the dimensionality then? Let's see. Start it over. Whoops. 5. Okay. So if you work it out, the spin 0 subspace of, you know, 6 spin half particles is 5-dimensional. And so we constrain ourselves to work in that subspace, and we get this space of like 6-dimensional quantum polyhedra, each with area 1/2 of each of the faces. And we can measure it and stuff. Like, let's do another one. Like, let's do like, okay, like a spin 1 and a, you know, how about 2 of the faces are spin 1, 2 of the faces are spin 1/2. How about that? So we get this guy, and you see, yeah, like indeed, you know, we got, you know, this face and that face are quite big. Those are the spin 1 faces. These are clearly the spin 1/2 faces. If we look at the dimensionality, oh, it's also 2. And, you know, we can evolve it in the same way. Look at that guy. He's just pulsating. You know, when it flips the fuck out there, you know, you see it kind of like, it's like, you know, that's because it's for a second there, you know, forms like a degenerate polyhedron, you know, which is essentially a polygon in a plane, and like maybe, you know, it's incredibly like big in that, you know, like wide polygon or whatever.
Is there any way to add any gravitas to this talk by taking us to the big dance, which is the big bounce and the absence of singularities?
Well, you know, I mean, that is like one of the reasons that the loop people like this kind of thing, where they're like, you know, they see in like a sort of atomicity in space. In other words, you know, you can't have space smaller than, say, what's the simplest case? A quantum tetrahedron with spin 1/2, you know, on each of the faces. In other words, like that's an atom of space. It's the fundamental smallest unit of space. You can't have a volume of space smaller than that. In fact, that's like what defines a volume of space in a way. Like you, in addition, you can define like volume operators, by the way. It's not something that I did here, but you know, it's something you can do.
Matthew, is that, are you saying that when you quantize space, that you have to assume that the angular momentum of each quanta of space is 0?
Yeah, except that, you know, you're not really interpreting it anymore as necessarily being like about spin. In other words, it's the same mathematics, but it's like, if you think about it, instead of interpreting this like, you know, spin as a quantization of the 3 vector, which is like the rotation axis of the spin. Instead, you're interpreting the same mathematics to be a quantization of the 3 vector, which corresponds to like a face normal or whatever. Although, as I say, that it's like a little bit not exact, because you can't interpret the expectation values of x, y, z as like being the face normal. So you got to do this little trick with the inner products. But yes, that is the idea. From the loop perspective, a state of space is given by a spin network, which is a graph. On the edges of the graph live like spins, and the vertices of the graph correspond to angular momentum conserving interactions or whatever. Okay, so that's like a spin network. Penrose, was thinking about them as early as the 60s. It's then reinterpreted by the loops people as being a state, as I say, of space, where the edges represent like fluxes of area, and the vertices represent little quantized volumes of space. And what's cool is like, what from one perspective is the conservation of angular momentum becomes from this other perspective, just very naturally, the closure constraint on the polyhedra. And so, you picture a state of space as being like some spin network, little polyhedra living at each of the vertices. You can contract them together. You can imagine, superpositions of, spin networks with different graph structure. You can imagine trying to evolve them in time, thinking about your spin foam stuff, fix a spin network, over
So
here.
does that rule out wormholes?
Sorry?
Does that rule out wormholes?
Well, it doesn't really rule out wormholes, in the sense that, in fact, it makes them somewhat more likely, right? In the traditional, like, what you mean? Like in the semi-classical kind of space, right? It's like the spin network would be like the most boring spin network that you could imagine, right? Like it would be something like, a grid or whatever of particles, or sorry, of like little vertices, right? So, it would be like, it's like a fabric, right? And like at each one of these vertices, there's 4 guys coming in. So there's like a little tetrahedron that lives at each of these, vertices and, whatever. And like, this is obviously, well, not obviously, but like, one of the things they try to do in loop quantum gravity is like from these like sort of considerations of the supposed microstates of quantum gravity, try to be like, well, in the limit, it's going to reproduce general relativity. And like, that's, one of the things that's always under active discussion. But, but like, one of the things you could say is like, well, any old spin network is fine. Like, what if they're like, weren't, what if these weren't here or whatever? Or what if, they were there, but, there was also like, a little wormhole that just, led over here. Why not? You just like imagine any freaking thing you want, basically. So yeah, like the wormholes are just sort of built in, right? Because you're just thinking about the connectivity of space as just being a graph, right?
Is this you speaking, or is this
however you like?
Is this you speaking, or is this Ravelli or any of his colleagues? Because specifically, one of the reasons for it is to do away with Big Bang singularities as well as black hole singularities, which virtually everyone now is dismissing in physics. And so why would wormholes still be plausible if singularities are not plausible?
Well, I don't see why there's a relationship necessarily between them. All a wormhole is a shortcut from getting, between 2 places. You know what I mean? Like, the original metaphor. It was John Wheeler who came up with it, right? It was like, there's an apple, and there's like a little wormhole. And, you know, normally you'd be like, oh, I gotta go, if I want to go from here, I gotta go like around, take the long way around. But, you know, maybe there's a shorter path.
Yeah, but one of the theories is that it's the singularity in a black hole that makes a wormhole possible. So if the singularity is gone via loop quantum gravity, how can there be a wormhole?
I don't think that the two are necessarily connected. I mean, after all,
I'm not saying they are. I'm saying I said one of the theories of the wormhole.
I mean, it seems to me that to even like have a notion of a wormhole is like with reference to like a semi-classical approximation of space-time, right? Like if instead of like, oh, there's like this, like the surface of the apple is like the more or less classical part, and you're like, oh, turns out this part of the apple and this part of the apple are like connected. But if there wasn't like an obvious, you know what I mean? Like imagine it was just space was just like a fucking graph with just like nodes just like randomly connected together. Are there wormholes? Is there a coherent fabric of space and time? No, I mean, it's just a graph, some parts are connected. You see what I mean? It's like to define a wormhole is to like define it like with reference to there like being a limit in which, you know, space-time is like what we normally think of it like. And again, like we know from things like quantum teleportation that this idea of like things, you know, disappearing over here and popping up over there are pretty ubiquitous. Like I mean, where, you know, if I do a quantum teleportation, like where's the singularity there, you know? Doesn't seem to depend on that. But
Can I
yeah,
ask you something, Matt? You know, you referred to quantum teleportation several times. Now, the quantum computation definition of quantum teleportation is not the same as the Star Trek
no, not at all.
definition. Which one are you talking about?
Aha. Yes, well, you know, to be fair to Star Trek, I mean, I don't know if they ever really go into the details how, you know, the teleporter works. But yes, you know, the relevant thing for quantum teleportation is that there has to be a prearrangement between the source and the destination. They have to share entangled particles in some way. And they also have to be able to classically communicate. And if those two conditions are there, then a quantum state that starts out at A can pop up at B without apparently having been transported between.
But is that limited by the speed of light? Because in quantum computation, the way you can have a teleportation circuit, but you've got to transmit a classical bit. So it's limited by the speed of light. Is that what we're talking about, or are we talking about something that's not?
Yeah, no, you're definitely right. You know, you could, so, I mean, in theory, when you think about the teleportation thing, it's like, you need to send a signal in order to tell the person at the destination what correction to do, okay? And
Right.
the correction you do depends on the answer that you get to the joint measurement that you do of the particle that you want to send and, in a way, the mouth of the wormhole or the entangled particles. So, you know, arguably, you could like regard like the teleportation is happening for you at least at the moment that, you know, you at the source make your measurement, and then it's already over there at the destination or whatever, you know. But you know, it's just a question. It's like, is it usable or not? It isn't really until you send this correction. In the case of, you know, in the case of teleporting one qubit, you know, you get one of the 4 Bell states, and you know, if you get the 1 Bell state, you know, you don't even need to correct it at all. So I mean, like, you know, for example, you could just sort of change the protocol a bit, right? Just do the experiment a bunch of times, but only send the signal like when you get the up plus down Bell state. You don't even have to say what the correction is, because in that case, the teleportation will always work. But yes,
All right. Now here's the thing. You know, a lot of people claim that you can teleport through a wormhole and it will appear on the outside of the other entangled black hole. Is that possible? How is that possible that it could appear on the outside? It's still contained. Everything is contained within the two black holes, between the two horizons. Is that correct? Although some claim that you can
totally.
send information from one out to the outside of another black hole.
Absolutely, yeah. So now I don't know exactly what the loop picture is on this. Again, you know, the loops people have their own way of dealing with black holes, with you know, these singularities at the core of black holes, with with Big Bang singularities and stuff like that, which, you know, you can think in essence of like they can avoid like a literal singularity, a place where space-time, you know, the curvature like diverges or whatever, because, you know, space for them is kind of granular, right? Like there can't even be like a smaller amount of space than this little Planckian tetrahedron or whatever. Okay,
It's
so like avoid these singularities that way.
But even beyond that,
centimeter. It's a cubic centimeter divided by 10 to the 99th is the smallest.
73rd.
space.
But beyond that, a singularity is a mathematical construction. A singularity cannot possibly, it doesn't have any meaning in the real universe.
Yeah, I tend to.
This is the point.
Yeah, totally. Now,
it just means that our math is breaking down.
Yeah, I mean, I completely agree with that. Now, the loops people have, you know, their own kind of story about, you know, how to think about, you know, as I say, the singularity, about, you know, what is happening in the black hole interior, what is the relationship to the boundary of the black hole, like its event horizon. And in general, their story is like not exactly the same as the story that comes out of ADS CFT. There's, you know, some important differences and some similarities, and nobody really knows like
what are the differences?
So yeah, so from what I mean, again, I'm not an expert in the subject, but one of the things that was coming out, I remember when I was listening to some of these loops lectures, was that basically they had a different notion of how to interpret the black hole entropy. In other words, they had a different interpretation of Hawking's result and did not regard the microstates of the black hole to be interpreted as just those microstates living on the event horizon. So like for Susskind et al., for Maldacena, for all these guys who, you know, working in that framework, the more ADS-CFT inspired framework, it's like, you know, it's taken as a given that there's this sort of black hole complementarity. In other words, what goes on inside the black hole is just what's happening on its event horizon plus the Hawking radiation. And that's not exactly the point of view of the loops people. Okay. So
let me ask you, so how does a loop quantum gravity treat Hawking radiation? Can they justify it with loop quantum gravity?
Yeah, they have a story about that, but I don't know exactly what it is. I'll try to find a paper where they explicitly discuss that. Like I forget. I mean, I've heard several different proposals, and I just not.
I mean, are they doing that for political reasons, or is this a natural outcome of LCG or LQ?
LQ. Well, yeah, LQG.
LQG.
Quantum cosmology. Well,
because, you know, some of us don't believe in Hawking radiation. We think the whole thing is a fabrication.
Well, so, I mean, we'll talk about, you know, what is the motivation of Hawking radiation? And, you know, it's the idea that basically accelerated observers would describe different vacuum states.
Right, and that's Unruh. That's the Unruh effect. So in reality,
Yeah.
this is the interpretation of the accelerating observer. In reality, Hawking radiation does not arise from any quantum effect at the horizon. Yeah, Unruh radiation.
The story is different. Hawking came up with his radiation strictly from quantum field theory. He solved the equations of quantum field theory in a curved space-time. Quantum field theory, this was the basis.
Yeah.
No, I understand that, Moshe, but it doesn't mean it's valid. Because again, if it's the Unruh effect, then it's only in the eyes of the accelerating observer, accelerating away from the black hole. It is not, and again, there's no experimental evidence. So, we're talking
Well,
the
it's
Delta
interesting.
9.
Right. So, the Unruh effect as, traditionally proposed, is one where, I mean, mathematically, essentially what you're doing is you're saying, like, I have a bunch of creation and annihilation operators for different modes of the Minkowski vacuum as seen by an inertial observer. And then I have a bunch of creation and annihilation operators corresponding to the different modes of, say, an accelerated observer, like in a Rindler spacetime or something. And then there's going to be a Bogolyubov transformation, in other words, an implementation of a kind of symplectic transformation that takes you from the creation operators as seen by the inertial guy to the creation annihilation operators as seen by the accelerated guy. And you can show that, on like the one state where, the Minkowski guy sees, no particle, no particles, the accelerated person on the same state will see some particles. And, what's interesting about that is like the way that like the different parts of Minkowski space and the different parts that like have to do with matter and antimatter, it kind of like scrambled up. And, the Rindler observer, of course, because they're constantly accelerating, have to describe the world as like being kind of divided in two, because there's like a part that they will not forever be out of causal contact with. And so because of that, they have to describe their portion of the world as a mixed state, not a pure state. And, this gets at part of the reason why they...
Okay, and there are two problems. There are two problems with this. One is if Hawking radiation exists, even according to the quantum theory, you would have an equal number of particles and antiparticles created, and probabilistically, an equal number would fall back into the black hole as escape. So you would have annihilation of these particles. But what you said is, you go from a pure state to a mixed state, which violates singularity, and also every way we represent the horizon is in the infinite future, which again violates causality.
Okay.
So what are we talking about?
Yeah, this totally. Again, I was just really speaking about the Unruh effect.
Oh, yeah, the Unruh effect is real.
And certainly, it's like...
It's in the eye of the accelerating observer. It's a back reaction to the acceleration. It's only in the eye of the accelerating observer.
Michael, talking about horizon, what matters for the Hawking radiation is the fact that what you usually refer to as the event horizon is actually the apparent horizon. The apparent horizon is real. It does not depend on the future. The apparent horizon is here and now. It just so happened that the apparent horizon and the event horizon coincide for most of the life of the black hole. So usually we just use the term event horizon. But as far as my understanding is that the event horizon is not relevant to Hawking radiation. It is the apparent horizon that's relevant. And this is where you get your radiation from.
Okay, but Moshe, with all respect, this apparent horizon was invented by Susskind to justify an incorrect theory.
No. You're confusing.
But even
one moment. The apparent horizon is nothing to do with Susskind. The apparent horizon has to do with Schwarzschild, not Susskind. Susskind has nothing to do with it.
Well,
You
I don't think
talk about some-
Schwarzschild was alive at the time.
you think about something completely different that Susskind has invented. You think about the extended horizon.
I'm sorry.
The extended horizon is a Susskind invention. The apparent horizon comes straight from the Schwarzschild metric.
Yeah, but you're assuming a you know, with black holes, you are always assuming a singularity at the center of the black hole, which sucks in all the mass. A singularity is not a physical thing, it's a mathematical construction. How do we know that a black hole it has a surface? It doesn't have a horizon. It's got a material surface.
Right. Well, so can I say a couple things? One is that, even in the case of the Unruh effect, you're making the somewhat unreasonable assumption of a constantly accelerated observer for all time. So, I mean, even that is like kind of an insane.
No, but to be stationary with respect to a gravitational object, you have to be accelerating.
True. I just
fall in.
It's like it could. Those things maybe change their acceleration once in their lives. So that's one thing. Another thing is to say, like, I feel like you agree with the black hole complementarity principle, which is to say,
No.
at all are like, no, don't worry about the singularity. Everything important is happening on the surface. I mean, that is how they look at it.
But you're creating just as many particles as antiparticles. So just as many fall in, antiparticles and particles fall in as remain above the surface, which recombine. So where do you get the radiation? And by the way, these are all virtual particles.
Yeah, no, I remember thinking about this myself. Yeah. Why is that not true? I used to know. Yeah, I mean, because you're basically saying, like, right, so like the traditional way people talk about Hawking radiation is something like, oh, there's like two particles that pop into existence, matter and antimatter, like right at the event horizon. And like one of them trapped behind the event horizon, like one of them like stays outside, and like the other one goes off, and like that's the Hawking radiation. And it's like, entangled with whatever went inside. But then you're like, well, but like, why would that make the black hole like evaporate, since like you've just like added a particle to the outside?
Why would only the real particles remain outside? What about the antiparticles? Why do we assume that only the antiparticles get sucked back in and not the real particles?
Michael, we use the word particle in a generic sense.
I mean
particle stands for particle and antiparticle.
No, I mean, you're right, correct. I was mistaken. Why is it we assume that the particle is the one that remains outside and the antiparticle gets sucked in?
No, we never assume this.
Then where does the radiation come from?
From particles and antiparticles. The radiation consists of equal numbers of electrons and positrons.
But they recombine. They would recombine very quickly.
No, they can be emitted hours apart. They can be emitted days apart. I emitted an electron now. Next week, I'm going to emit a positron.
Yeah, but you know something? All of these particles start out as virtual particles. And virtual particles don't live for very long.
That's the whole point. Near the horizon, they start as real particles. Actually, this is what's really misleading here. Outside the horizon, they can only be virtual particles, and you don't, as far as I can tell, you will not get any radiation there. The only way to get radiation is if one particle starts outside and one starts inside. The one outside is a real particle with positive energy. The one inside is a real particle with negative energy. Energy is conserved. The one with negative energy falls into the singularity, which loses mass. The one outside with positive energy escapes, and this gives you the radiation.
But Moshe, why don't real particles form inside and I'm sorry, why don't particles form inside and antiparticles outside?
Who says they don't?
Well, then
Who
they
says-
would recombine.
No, no. If you have a particle forming inside with negative energy and an antiparticle forming outside with positive energy, they don't have to recombine.
Okay, and what you're
They never
saying is,
recombine.
what you're saying is that there are antiparticles floating around in the universe.
You bet.
You know, there's no evidence for that.
They,
Well,
they don't, they
well,
don't live for very long because eventually they find a partner.
Yeah,
They're
like
not like you, Mike. They found a partner.
supersymmetric particles.
What?
Like they found supersymmetric particles at the LHC. Come on. There's no empirical evidence.
I mean, they see positrons like zipping along from, you know.
No, there's no antimatter there's no free antimatter in the universe. We can create it in the lab, but there's no free antimatter in the universe.
Is that true?
It doesn't exist for very long anyway.
Cloud chamber, you know, and look at cosmic rays. Every once in a while, you see a positron. Is that wrong? I mean,
They don't exist. If they exist in the real universe naturally, they don't exist for very long. And yeah, we can create them in the laboratory, of course. But we live in a particle universe. We don't live in an antiparticle universe. They would be annihilated very quickly.
yes, yeah, totally, yeah.
And
I mean,
that's the whole point. So where's this Hawking radiation coming from? It
Yeah,
would
I
be
think you're
annihilated
concerned. No, I
very
mean,
quickly. Besides, there are other issues. There's, you know, going from a pure state to a mixed state. I mean, there's so many violations here. There's violation of quantum physics.
Well, again, so I mean, people these days really feel like they've answered, you know, to some extent, a lot of these questions. You know.
Yeah, but they're all wrong. They're promoting their own careers. This is all political.
I don't know. I mean,
it's not.
So, well, I want to say a couple things. A, you know, in terms of just the Unruh effect, you know, there's been recent attempts to measure the effect in condensed matter systems where they can essentially have like a much lower speed of light. And so the Unruh effect is like correspondingly greater. And so they might be able to measure it there. So certain aspects of these things, you know, are becoming testable like in other ways.
The Unruh effect can be explained. The Unruh effect can be explained by Newton's third law. It's a back reaction to the acceleration. But it's in the eyes of the accelerated observer. It's not, the particles, the unaccelerated observer, the stationary observer does not observe the particles.
No, you have to be very careful about it. Michael, you're an electric engineer. You know very well that if you have an antenna going past you, accelerating, you will see the antenna emitting radiation.
Right, the back reaction.
This radiation will be in the eyes of the stationary observer. The accelerating observer is the one who's going to see the back reaction.
Well, back reactions take different forms.
The Unruh radiation, as measured by the accelerating observer, is going to be the back reaction to the radiation that is being observed by the stationary observer.
Well, you know, back reactions take different forms. They take different forms. But in that case, the accelerating observer would not see a current in the antenna.
One comment I was going to make about this issue about, you know, negative energy and stuff. So, like, you know, as I say, at least in the world of Susskind et al. And Maldacena and the ADS CFT and the holographic principle and the black hole complementarity world, you know, they basically are like, yeah, the singularity is not relevant. What happens in the interior is dual to the surface and, you know, the radiation. And that furthermore, you know, there are wormholes possible in a geometrical sense that occur, you know, like we talked about way back when two black holes are both entangled and also have a form of classical coupling or classical communication between them. And effectively the idea was that like the classical coupling acts as a kind of negative energy shockwave that, you know, causes the event horizon itself to like move back, thus kind of like revealing some stuff that was behind it, like kind of like the ocean recedes a bit and you see like some shells that before were underwater but now are just, you know, exposed to the air on the beach. And like this sort of negative energy effect is the reason why something can fall into a black hole on one side, and if that black hole is entangled and there's this classical coupling, it can pop out the other side. And the idea is it's just sort of like the geometric equivalent of doing, you know, a quantum teleportation protocol from quantum information theory, basically. So yeah. Now, again, in the loops picture, the idea of black hole complementarity is like it's not exactly the same as those proposed by those who work in, you know, this, you know, the whatever I call them, the black hole complementarity guys or whatever, the ADS CFT guys. So there's like, you know, a bit of a different picture there. But still, you know, there's wormholes, which, you know, they treat, like, as I say, they're perfectly able to treat because they view, you know, space as being a kind of like superpositions, a sort of like superposition of different like graphs that have these polyhedra living at vertices. And since they allow basically like arbitrary connections between, you know, different nodes on this graph, there's, you know, nothing weird in principle about having, you know, say like a fabric like structure with just, you know, like a wormhole that's just leading to kind of an unexpected, you know, connectivity. Now the question then, like if the loops people want to assume that, the ball that's in their court is to say, well, how is it then in the limit or the classical limit, we recover, you know, a smooth, you know, Einstein general relativity looking type thing, such that we like don't see a lot of wormholes at our scale or whatever. You know what I mean? Even if there are tiny little wormholes at the micro scale or something like that. So, you know, insofar as they allow, you know, arbitrary connectivity, they then have to explain how, according to their theory, you know, it all kind of cancels out to being like basically, you know, wormhole-less smooth space. So they sort of have that challenge.
I just found something rather interesting on a website called physics.aps.org rather than physics.org.
Yeah.
In which they say that loop quantum gravity predicts that space-time continues across the center of the black hole into a new region that exists in the future and has the geometry of the interior of a white hole.
Yes, that's quite true. So this was, you know, when I went to this Loops conference, this was something they were very excited about. So their idea is that, like, you know, so the ADS CFT picture, right, is that like what the interior of a black hole is dual or complementary to its surface and the Hawking radiation. It was more like in the Loops picture, it's like stuff falls into the black hole, but unitarity is preserved because it all pops out later out of a white hole. In other words, like a time reversed version of the black hole. So that's sort of like how they preserve unitarity.
Can I ask you a very simple question?
Yeah.
How does stuff fall into a black hole when the black hole has the maximum density it could possibly have for its volume?
It gets bigger when stuff falls into it.
It gets bigger. It doesn't fall in. It accumulates on the surface.
No, it does not accumulate on the surface. It falls in.
You're assuming a singularity at the center.
I don't assume
a singularity doesn't exist.
No, I do not assume anything in the center.
So where does the mass go? Where does the mass go?
It cannot stay on the surface. It cannot stay on the surface.
But you're assuming it goes into the singularity.
It goes into whatever happens in the center. What happens in the center, we don't know. You want to call it singularity? Be my guest. I don't have any
No,
objection.
I would refuse to call it singularity because a singularity is a mathematical construction
Okay,
that
fine.
doesn't exist.
Okay, call it whatever you want. It
So how
falls
can
into
the
the
mass go into the singularity? It gets destroyed at the singularity, but yet the black hole
It
retains its
falls,
mass.
let me say it for the last time, it falls into the center. We don't have the foggiest idea what happens in the center. The only thing that we know for sure about the center of a black hole is that we don't have the foggiest idea about what happens there.
Because
That's
Moshe,
it. We don't know anything else about it.
You have three logical possibilities. You have the possibility that there is a transmission beyond the so-called singularity into some kind of extra dimensional space or a wormhole. You have the singularity, which to me is an impossibility, which is a metaphysical concept. And you have the possibility via loop quantum gravity that there is a limit to the density of the matter and of the total mass that collects near the center of the black hole. And so it has some sort of size. What is that size? It can't be any smaller than the Planck length, according to loop quantum gravity. But if you think of it in terms of degeneracy pressure, it would probably have to be larger than that. For instance, what if it's a quark star?
all right, here's the
I think that's a good way of thinking about it, because it's like I'm saying, you know, mathematically, the loops people can avoid the issue of mathematical singularities because they view space as granular and it's made up of like these atoms of space, and like they can't be any smaller. So they don't have any problem with mathematical singularities. Now,
but again, Matt, we have no empirical evidence that space or time are quantized. And to answer Moshe,
well, can I respond to that really quick?
Sure.
So one of the things that the loops people were excited about when I went to this conference was the idea of, right, so like their position as against the like holography people is that, you know, the stuff that falls into a black hole, you know, unitarity is preserved because, you know, bits of it later emerge from like a white hole later on. And so, you know, they want to use that to think about, say, like the Big Bang, so that like they're viewing like the Big Bang singularity itself as a white hole. And one of the ways that they were proposing of testing the theory was to say something like, well, what if we have like a cyclic cosmology, so that we have like a white hole, which is like our Big Bang, and then there was like a previous universe where there was like, you know, a contraction, you know, kind of a black hole type thing. Now, if there were like other black holes in that old universe, pre-Big Bang universe, they could have made it through the singularity into our universe, leading to inhomogeneities in the cosmic microwave background radiation. And so, you know, not just the loops people, but, you know, Penrose and others have been pushing, you know, for this idea that like, if we can find, you know, degrees to, you know, if we can find, you know, certain angles, certain imperfections in the uniformity and things like the cosmic microwave background radiation, we could potentially explain it as, you know, shit from like the previous universe, making it through the so-called singularity into, you know, our universe at the beginning, and then those, you know, traces being kind of, you know, after inflation, being like smeared out across the night sky. So as I say,
the loop quantum gravity specifically denies the Big Bang. It calls for a big bounce in their conception, in their cyclical conception. It calls for a big bounce because there's a limit to the degree of density at the gathering point, whatever, in a cyclical process due to the quantization of space. So they deny us the singularity. In that sense, it's a matter of a gathering point of a certain hyperdensity, exponential hyperdensity. It's not a singularity.
All right.
as we
You know,
know the
a
answer yet,
cyclical,
it's a definite proposal. You know, it's like
a cyclical universe would violate entropy. But you mentioned Roger Penrose and his cyclical phenomena. His cyclical theory is conformal cyclical cosmology, where a previous universe crosses over into our current universe after all the black holes of the previous universe have evaporated and we have very low entropy.
I mean, I like that proposal because it's like, I think, I don't know exactly how it's related to the loop proposal, but I like that one because it's just sort of like, starts with this premise of just at a certain point, the beginning and end of the universe, like looking indistinguishable. So then you can just like glue them together, which just reminds me of
You
that
can glue them together.
Asimov.
You can glue them together by conformal geometry, because at the end of the universe, there's no space and time, measurement. You know, it's conformal. You get a transition from one universe to another that's conformally invariant. But here's the thing. I was gonna, what Moshe mentioned, and now I've lost my train of thought. But anyway, all this stuff about a lot of these theories are based on mathematical constructions, which don't necessarily relate to the real universe. Now, all these quantum theories of black holes are based on using the Schwarzschild metric beyond the, quote, event horizon. And I claim, as do many, that you can't do that. Because once you cross the event horizon, you have a Gaussian surface that's collapsing on you. So you can't use the same Schwarzschild metric that you were using outside of the event horizon. And then you got this thing with a singularity at the center that sucks up all the matter.
Yeah, okay, yeah.
It's nonsense.
Michael, we heard this.
Yeah.
We heard this many times. There's no need to repeat it. Let me just mention that I've heard an exciting, wonderful talk by one guy from Princeton. I could kick myself for not being able to remember his name. He was talking about a cyclical universe, but where the previous universe does not collapse into a singularity. The previous universe shrinks into a finite size universe that then grows to become our universe.
You're talking about Steinhardt, Paul Steinhardt.
Yeah,
that's
right. That's right, Steinhardt. That's right.
But Steinhardt is
Mike.
completely wrong. Penrose has it better. Penrose is conformal cyclical, where you don't have a collapsing universe that bounces back. You have a previous universe consisting of a huge black hole that evaporates, destroys all the entropy, and then you start all over with a new universe at zero entropy or low entropy.
I mean, the problem with the collapsing universes is that
violates entropy.
The omega lambda ratio doesn't work to give us this kind of cyclical universe. This is why Penrose has completely altered the theory of cyclical universes. So we're not. We're also in a flat universe. We're in a universe with acceleration of the expansion, a widening of the spatial dimension, and so this also, it doesn't seem to lead towards this cyclical universe, the old form of cyclical universe. This is the reason for Penrose's innovation.
And a collapsing universe violates entropy. It violates everything we know about physics. So Penrose's theory, at least, is consistent with what we know about physics. And it explains how we started at very low entropy, because this huge black hole evaporates and destroys entropy, destroys information.
Another, this is sort of related, but Ravelli has an interesting paper where he proposes a kind of different interpretation of entropy say, we have to regard the beginning of the universe to have been in some kind of like low entropy state in order to like, recover this idea that time goes forward towards.
Well, we know that for a fact. The beginning of the universe had a low entropy state under any theory.
Right. Well, so Rovelli in a paper says like, well, maybe that's perspectival. Like, in other words, it's not like objectively true that the initial state had low entropy, but that, you as like a part of the universe, like an individual observer, couple to the universe in some limited way. And therefore you, because of your particular coupling, are going to like coarse grain the universe in a particular way. In other words,
this is observer dependent, is what you tell him.
For him,
no,
it's
I'm sorry. The universe exists outside of our consciousness.
Well, he's saying that, no, but it's saying like the universe exists outside of our consciousness, but that the time direction, in other words, like the state which is assigned to be the initial state in the distant past is relative to the observer. I mean, that's not saying it's all just subjective, because you'd still be able to relate the different perspectives to each other.
There were no, according to a recent calculation, it was not until about 5 billion years ago. It's not just a matter of our star system and the evolution of life in our star system. It was not until about 5 billion years ago, if you make use of the Big Bang timeline, that life forms became possible in our cosmos as we know it. So as far as the observer issue, I mean, literally within the Big Bang cosmology timeline, an observer didn't become possible until sometime after about 5 billion years ago.
Oh, well, but I mean, doesn't really affect the argument, because it's just sort of saying, it has more to do with, memory traces, like the physical traces left by things, and the way that a given physical system, couples to the rest of the universe and is also attempting to like tell a story about its past or whatever. Or like, I'm not saying.
Matt, all of these crazy theories are merely justifications for why the original precepts of these theories are completely baseless. All of Susskind and all these modern physicists, because they've never discovered anything in real physics.
Well,
and there hasn't been anything discovered in real physics in several decades, in fact.
That's a bit of an exaggeration. But I will say this.
So they got to come up with crazy theories to justify their original crazy theories.
Well, I don't see how that's crazy. I mean, after all, history books are not objective, right? It's like a person telling a story based on evidence about the past. Like,
as Churchill said, the winners will write the history.
Right? So it's like, observers, we're trying to understand what like prehistoric man was like. Well, we don't have access to all the data. We weren't there. We like reconstruct a history of the universe based on bones we find, or,
He lives in the White House. He's alive and well.
Yeah,
he lives in the White House.
Alive and well.
We have not advanced one iota from prehistoric men. Because diplomacy, which is the only thing that will save us, has never kept up with technology. And that's why we're on the verge of destruction.
I can't disagree with you. Yeah, it's all too true. So, I mean, we're in the same situation, though, in cosmology. You know what I mean? It's just like we're telling stories about the past based on the evidence that we have today, and not just, any evidence, but evidence, from our perspectives, from not just the perspective of like being on Earth or whatever, but also, the perspective of being physical organisms who have a certain, way of processing time and space and memory and so forth. So, I mean, to me, it's not like totally crazy, because otherwise, you have to assume that, like, you have to take as axiomatic that the initial state of the universe was low entropy. And like, why would that be? I mean, if there's going to be an explanation of it, well, what would it look like?
Well, Penrose explains it in his
I
CCC.
do like that. Yeah, that does. I vibe with that. Like, I'm okay with that idea.
Yeah, and I got to say, Penrose, Hawking was in awe of Penrose. Penrose was not in awe of Hawking. Let's get that straight.
Hey, I'm in awe of.
But here's the thing.
It strikes me in the, that if you have a Big Bang cosmology and you accept that, and I don't, but if you have a Big Bang cosmology and you accept that, it occurs according to a timeline in which you get various forms of symmetry breaking, and you get the four forces emerging, and you have a quark gluon plasma, and later on you have nucleons, and later on you have atoms forming, and later on you get higher degrees of organization via a planetary nebula and star formation and galaxy formation, and then galactic clusters and the WIM, all creating greater and greater degrees of structure over a very long period of time. How can you talk about moving from a low entropy state to a high entropy state? There is a process by which you arrive at a very high degree of organization, the same high degree of organization.
Look, Victor, the stars, the sun and the other stars put out very low entropy energy. Religionists have tried to use this argument you're making, that God must exist. God must exist because otherwise what happens on Earth, the complexity on Earth, would be a viviolation of the second law.
That's not my point of view.
And that's not true. The stars put out low entropy energy.
No, what's interesting is, like, you don't even, as far as I know, you don't even need to talk about the stars. It's like, yes, it's certainly true that if you look at, the history of like life or whatever, it seems to be one of increasing organization. Like, look at this body, it's so organized.
Because the sun is giving us low energy entropy.
Even us. In other words, we produce more entropy than is, like, our bodies are low entropy. Like, in other words, we shit. You see what I'm saying? Like the process of maintaining this local low entropy body is offset by the amount of pollution that I'm exporting into the world.
But the sun replaces all of your entropy with low entropy energy.
Michael,
this is the point. You and the Earth don't exist in isolation. The sun is the major factor here that puts out low entropy energy and enables complexity to develop. When the sun burns out, then everything is dead.
Michael, if we're moving towards, an entropic state, whether that entropic state is the big chill or the big rip.
What you mean we? White man?
We in the sense of the cosmos. If we are moving toward an entropic state that is either that of the big chill or the big rip, what you have in a Big Bang cosmology is an initial state which resembles that of the big rip. You do not even have baryons yet. You do not even have atoms or molecules or macromolecules or organic molecules or planetary nebula, stars, or galaxies.
Victor, you need to read Penrose. Google it, conformal cyclic cosmology, CCC.
I know Penrose's idea, but I'm talking about.
No, but what you're saying is conflicting with Penrose's idea.
Address this, Michael. I'm describing a very good physical analogy between the state that exists shortly after the Big Bang.
All right, but you have to go.
Listen, wait. Let me finish. And what we call the Big Rip, which is even a more entropic state than the Big.
That's bullshit. The Big Rip. I don't even know what that's bullshit. Look,
the Big Rip is when the particles themselves tear apart once you have an.
Because everything's expanding too quickly.
All right. Here's the thing.
Themselves tear apart.
Now here's the thing, and this is what Penrose thinks: that a black hole does not have entropy. Information entropy is destroyed in a black hole. And ultimately, at the end of our universe, or any universe, all of the matter congeals into a huge black hole, which evaporates. And so this is how you destroy entropy. So when this final black hole evaporates after 10 to the 100th years or whatever it is, you are left in a very low state of entropy. And that can cross over conformally into a new universe.
But you have different scenarios. You have the big chill, which is the more common one.
But this is all nonsense.
It's not all nonsense. Will you stop with it? You don't know. You don't know.
Nobody knows.
You state things with like absolute certainty all the time.
None of us has absolute certainty. None of us knows.
Oh, thank you. So I just began by telling you that I don't even accept the Big Bang cosmology. So all I'm doing, let me talk. Let me talk. So all I'm doing is describing models. They're not my specific models. They're cosmological models. I'm not making assertions, and I'm not making trumped up assertions in the manner of what you do quite often, Michael. It's not a matter of injecting controversy into the discussion. You inject that, at times you make absolute assertions.
No, absolutely
you gotta
not.
step
I
back.
don't believe anything is absolutely
correct. You gotta step back, really.
Wait, so I have a question about the cyclic cosmology, because it seems to me that, it's a sort of general rule that, given, entropy will only increase for an isolated system unless you wait for an occurrence time. So is the idea that, like, I guess I see two possibilities. One is that, Penrose is saying, at a certain point, you end up in this like very high entropy state with respect to the beginning of that universe, but that when you consider that state, like with respect to this like future universe, it looks like a low entropy state.
No, Matthew, that's not what Penrose is saying. Penrose is saying that black holes destroy information, which is contrary to what a lot of knuckleheaded physicists believe today, that you can't destroy information. Black holes destroy information. At the end of the universe, you have this huge black hole that's been congealed from all the matter in the universe, and it has destroyed all the information. So it's got a very low state of entropy. Then as it evaporates, whether it's Hawking evaporation or what have you, you can transition into a new universe at a very low entropy. And there's no question that that entropy is increasing, because that essentially is the vector of time. There's no question that whether you believe in the Big Bang, this popularized version of the Big Bang, which is nonsense,
well, so
or not,
that seems to suggest that
we still started at a low state of entropy, and it's because whatever came before destroyed the information of the previous universe.
Well, but it seems to imply that, like, indeed, entropy is like not objective, but is perspectival. Because it's basically saying something like, as the universe goes and like dies this like black hole heat death or whatever, like saying like the universe is so like fucked up and like whatever gaseous at that point, then like there isn't even enough structure to have clocks or to have sufficiently complicated beings which could compare the current state of the universe with the previous state of the universe and realize, oh, entropy is increasing as like the second law of thermodynamics says it should. In other words, you get to a point of such disorganization that there aren't even clocks anymore, no even way to measure entropy, and that therefore the universe has the potential to start over because, I mean, then that's just like a state of...
But the point is that the entropy is destroyed in a black hole. which is not what most physicists today believe. But the entropy is and Penrose believes this. The entropy is destroyed in the black hole. Now, even if we take Victor's proposition that we end in a big chill where everything just gets torn apart.
No, that's the big rip. That's the big rip.
Still a low entropy state, and we can start all over again from a low entropy state.
Okay, so the notion that everything gathers into a massive black hole is
I'm
not.
sorry,
Is that
I can't hear anything because there's a fire truck outside
it's
my
not
window.
merely counterintuitive. It's an antithesis. It does not describe the universe that we live in. The universe that we live in is one in which the capacity for star formation in the galaxies is diminishing.
Yes.
And at the same time, the galaxies are moving away from one another, and the rate of expansion is greatest at the furthest points in the observable universe, and we're living in a flat universe, which is likely geometrically infinite, and therefore we do not know what the nature of the universe is beyond us. But what we do know from what we can see in the observable universe is an expansion.
Yes.
And the notion is that at a certain point, if this expansion continues to accelerate, it's already beyond that of the speed of light. At the limits, it's already beyond the speed of light. And so eventually, in that scenario, assuming that this is physically possible, first you would have a disaggregation of all of the star remnants, whether they are black holes, whether they are neutron stars, whether they are brown dwarfs, whether they are black dwarfs, whatever the state of those remnants are, they would begin to tear apart. And then you'd have a further acceleration of the expansion of space. Then the aggregate particles, the composite particles would tear apart, and eventually perhaps the particles themselves would tear apart, and we would begin to answer the question, which we can't answer because we do not have particle accelerators to do this, if there is, as at one point Einstein postulated, an infinite number of sublevels at the subatomic level and at the subatomic level. In other words, you'd get a tearing apart of all of what we see as fundamental particles into smaller and smaller particles, and then perhaps you wouldn't have any particles, you would just have a heat death, a total heat death, not just that of the big chill, but that of the big rip.
Which leads to low entropy. What you're describing is a progression towards low entropy, however you get there. But the physics indicates that all the matter in the universe would congeal into a huge black hole before this big rip. But in either case, you would wind up in a state of low entropy.
There'd be no single black hole because of, based on what we know now, based upon the omega lambda ratio, there cannot be a single black hole.
Well, I'm not sure that's correct, but in either case, you would have low entropy.
It's an expanding universe, unless if you postulate, and it's possible, unless if you postulate that, for instance, the ratio between, dark energy, which is actually increasing, the amount of dark energy is actually increasing, because if dark energy bears a relationship to the vacuum energy, and if space is widening at the present moment, which it seems to be based on most observations. There is a cosmologist who says no, but he's highly controversial. So if this is the case,
it ain't
you would have to have the equivalent of some process occurring within dark energy to the process that occurs in inflation, where dark energy would then suddenly reverse when it reaches some phase. That would allow for a cyclical universe, a big bounce, big a big bounce cyclical universe would be
Victor,
possible.
there's no evidence. The evidence we have is that the universe
I'm
is
not saying
expanding.
there's evidence. I said you would have to postulate a change.
Why would you want to do that?
Well, we have already postulated. I'm not trying to do it.
The
I'm
universe
just,
is expanding at an
I'm just-
accelerating rate. The
Can
Nobel
you-
Prize has been
Can
awarded
we
for
just
that.
talk without making everything a polemic? Can we just use models without making everything a polemic? I'm just postulating a model. I'm not saying it's my model. It's not. Can we? Everything doesn't have to be a polemic.
Yeah, but in science, you know, you can postulate every mathematical model you want, but in science, there's got to be some empirical basis for the model. And unfortunately, for the last 2 or 3 decades in physics,
here's an empirical basis. Here's an empirical, not a basis, but empirical analogy. The empirical analogy is inflation. The empirical analogy is the increasing acceleration of the widening of the universe. It is the alteration in the amount of dark energy versus energy. It is so in other words, the universe is not in some static state. It's in an evolving state, and it's gone through, according to inflation theory, if you accept that.
of course.
That's a big if. If you accept that, we have a cosmology which has gone through very significant phase changes. So all I did was throw out the idea. I do not believe it. I don't believe anything in the realm of cosmology. I think it would be presumptuous. So I tossed out there the idea.
But the cosmological constant has been shown to be true. The Perlmutter group won the Nobel Prize. There's empirical evidence. Yes, there is a cosmological constant, which you call dark energy. But it's a natural result of the differential equation, Einstein's general relativity equation. You can always add a constant to a differential solution of a differential equation.
Well, but why that value, I guess, is the question.
They keep measuring it, the cosmological constant at a different value.
Yeah, totally.
And given the phase changes that we pass through, it is possible to postulate without any belief. It is possible to postulate that there would be some shift later on in some later phase in the very nature of dark energy that could cause a more classical cyclical
So what are you saying? The
cosmological
cosmological constant can become negative? Is that what you're saying?
Maybe there's a limit to it. Maybe it goes through the opposite of inflation.
And maybe if my grandfather had tits, he would have been my grandmother. There's no empirical basis
If your
for what you're
grandfather had
saying.
tits, he'd be Tiresias.
You know, we
And he
can
would have
only
made his
go
way
on what
to the
we have an
wasteland.
empirical basis for. And, this is the problem with physics today. They come up with all kinds of crazy theories which they know can't be tested and for which there's no empirical basis.
To be fair, I mean,
we've heard that before, Michael. We know.
But that's the point.
To be fair, it's like several different groups have measured different values for the cosmological constant. And
Right.
like, there's a question about how to make their results agree. What are the different techniques they're using? Is it possible that it varies from place to place in space? It's even
Of course
more
it varies from place to place.
I'm just
But
saying
that
it's
isn't the point.
more complicated than
The
just
Nobel Prize has
know
been
the
awarded to
value
the Perlmutter group.
Well, but even that result, that's what I'm saying. It's it'd be one thing if it was Perlmutter, measured lambda to whatever, and now we have to explain why it's that value.
You can only measure it at very great distances.
But it's even
It doesn't show up except at great distances because it's so small.
I'm just saying that there's disagreement about even what that value is right now. I mean, we know it's not 0. But
Well, of course there's disagreement, but we know it's positive.
It's somewhere between 68 and 75 kilometers per second per megaparsec.
What can we measure 100% accurately? There's nothing you can measure 100, but we know it's positive, we know it exists, and we know the expansion of the universe is accelerating.
Well,
There's no question.
believe me, there's actually some serious discussion going on in international fora of a theory that we are completely misreading the redshift. And therefore, we have not verified anything close to a cosmological constant or whether the cosmos is expanding. I'm absolutely sure. I
Yeah.
highly
no
doubt this, but there's
Hubble
serious
showed that.
discussion of
Hubble
this theory
showed it was
going on.
expanding.
There's serious discussion of this theory going on.
All right, let me ask you something, Victor. Do you believe in the Higgs boson?
You mentioned it last time. I think we have evidence of a particle. One second. We have evidence multiple times of a particle whose mass is nearly identical to the mass that was foreseen by Higgs and his colleagues back in the early 1960s.
Okay. Do you know that Carlo Rubbia, let's talk about Italian scientists, Carlo Rubbia, who runs Carlo Rubbia, who runs CERN now, is a very well-respected scientist, claimed in 1984 that he had discovered the Higgs boson at 1.5 terabyte TeV. And it was later proven wrong. Now, the evidence we have is all based on statistical fluctuations. And by the way, now they're saying there's got to be, wait, let me finish. They're saying, but we have several bumps. There's at least 2 or 3 Higgs bosons because the statistical data is so fucked up. You know what the real issue is here? They expected, when they started the LHC, they expected to find supersymmetric particles. Oh, we're going to find supersymmetric particles right off the bat because they're at low energies. Didn't find the one.
Here's something that I've been meaning.
Let me finish. And so they were under political and economic pressure to prove the Higgs boson. Prove the Higgs boson. The Higgs boson is based on less than a 2 sigma, on a 1.8 sigma verification.
But if that theory is true,
when the standard is 5 sigma.
Like, why would they have bothered to shut down the LHC for that year? You know what I mean?
Why did they shut it down? Because it wasn't working. Because they fucked up. Because the engineers fucked up.
Okay,
their wires crossed.
Please.
Is it like a little animal?
What does that have to do with what I'm talking about?
Michael,
the whole basis. It was a political decision to make this announcement.
Down. Michael, be calmer.
It was a political decision to make this announcement because they were in jeopardy of having their funding cut off when they didn't discover any supersymmetric particles.
Okay,
just like the super collider in Austin,
Texas. Let me say something about.
There's so many people. There's fucking thousands of people.
There are 3 bumps. There are 3 bumps. And the best they have is 1.8 sigma when the standard in physics is 5 sigma. There's only a 1 in 15 chance that the Higgs particle has been confirmed.
Let me say something. Me say something, Michael. You've been.
I'm not saying the Higgs particle.
You're filibustering. Let me say something.
But their conclusions were based on
Let me say something.
Okay, say something.
Let me say something.
Yeah.
About the whole notion that goes back to one of the initial questions that we were asking in this entire series, which is the issue of measurement. And I wanted to, relating it to particle accelerators, taking it beyond the issue of measurement at the quantum level in the sense of the way in which the measurement alters the nature of things, okay?
Oh, come on.
Let me say it in the sense of measurement as detection and in the sense of detection of particles and of the properties of particles and of the nature of particles. Okay, so let me finish. Yeah. So the issue is that when discounting for the moment the existence or non-existence of dark matter, okay, which is coming into question in recent years. And let's just look.
Oh, dark matter is complete bullshit.
So the baryons okay, of which we are made, of which the visible matter in the cosmos is made, are most of the mass by far of baryonic matter, which includes leptons as well.
And by the way,
so
that
let me finish the idea. So
that mass is not due to the Higgs particle.
Filibustered for 20 minutes.
That mass is not due to the Higgs particle. It's due to the.
Let me finish, man.
Yeah.
Let me finish. So what we've got in terms of our observation of quarks, okay, which are the basis of, they gather into 2 ups and a down, or 2 downs and an up, in the proton and the neutron, okay? And then the strong force actually creates most of the mass beyond what the Higgs is creating from the, is lending to the quarks. So what you've got is most of the mass of the universe are in the nucleons, and yet we have never observed quarks and the strong interaction directly within the nucleons. All we have seen is quarks in a quark gluon plasma for nanoseconds, okay? That is all we have seen of the quarks. We know virtually nothing of the quarks. Our entire model, which is the basis for by far the lion's share of the mass in the cosmos, is based upon pure mathematical models. So what we've got is a situation, I'm anything seconding what you're saying about the Higgs. I'm saying that what we're using is pure mathematics to explain the essence of the universe, meaning its mass. I mean, it's not an intrinsic property of matter, but it is the basis of the interactions that are occurring.
And Victor, how many Higgs bosons do you believe in? Do you believe in one, or do you believe in the Trinity?
I believe in the Trinity. And I believe in the archangels, the angels, the seraphs, the cherubs, the thrones, the dominions, all 9 choirs of Higgs bosons.
After CERN made its self-serving announcement of discovering the Higgs, which even surprised Peter Higgs, now they're saying, but there were 3 bumps in the statistics, none of which are statistically valid, so there's probably more than one Higgs boson. And by the by, if the Higgs boson is what created mass, do you know that the vacuum energy, the cosmological constant, the vacuum energy would be up to 120 orders of magnitude greater than what it is, precluding any life in the universe, precluding a universe. I mean, these are all bullshit theories that don't have empirical evidence.
Measurement,
I think that one of the things that separates the Higgs boson case from the cosmic expansion cases, we observe like the redshift in the case of like the cosmic expansion, and redshift, what does it really mean? I mean, it's like it means because things are moving away from us, or the space in between is accelerating, but I guess
we can only base it on our best previous experience that we know, and to come up with a mathematical theory and then try to manipulate the statistical data to prove this mathematical theory is not science. This is politics.
Look,
now, I'm not saying the Higgs boson is not real.
Unlike the ancient theory of epicycles, at the very least, you can say we have multiple mathematical theories that physicists are trying to hack away at to explain the data.
Yeah, so we also have Technicolor. Do you believe in Technicolor?
One math theory, and like everyone was like trying their best to like, make sure this emperor with no clothes like stayed robed or whatever. But hey, we got like a lot of mathematical theories that people are hacking.
Well, like I said, Carlo Rubbia, who's the head of CERN, in 1984, he announced that he had discovered the Higgs boson. This is the pressure that they were under, and he had to retract it because he was wrong.
But the mass there did not align with the mass that was foreseen
According to
by
whose
Higgs.
calculations. And now we have 3 bumps in the data. We've got 1 from the CMS line, and we got 2 from the Atlas line at CERN. And so are there 3? Are there 3 Higgs bosons? And by the way,
We
none
have
of
a
them.
W. We have a W boson and a Z boson
Right.
for the weak
That's not
force.
great.
We
And
also
this
have
is the issue.
how many different kinds of photons with
And
differing photon energies do we have?
And
So-
this is the issue. They had to invent the Higgs theory, and along with symmetry breaking to explain the masses of the W and Z bosons. That is the main reason. And a lot of physicists say Higgs is bullshit. It conflicts with too many things, and there's got to be another explanation for the masses of the W and Z bosons.
Philosophically, though, I mean, I think part of the issue is that people like massless theories, and they always want to explain a theory with mass as like some extension of an intrinsically massless one.
Oh yeah, well, a gauge theory has
Let
to be
him finish.
massless.
Let him finish, Michael.
A gauge theory has to be
Michael, let him finish.
massless. Oh, come on.
But just that. I mean, I'm just saying, like, I think that's like an underlying, motivation in general, like start with a massless theory.
A gauge theory has to be massless. And when they realize that the weak force acts on very short distances, that can only be explained by bosons, massive bosons that mediated the force. So they had to come up with a theory to explain the masses of the W and Z bosons.
The possible fifth force, which has just been discovered over the past 4 years, and there's
A fifth force? They haven't explained
yes,
the fourth
and there's
force.
several verifications. Is X17? It is almost 17 mega electron volts, and it is similar in a certain sense to the weak force, in the sense that it is a decay process. In this case, the decay of a beryllium-8 atom, and so this is another possible boson with mass.
Yeah, I mean, why stop at 4?
No. A boson can have mass, but a boson that mediates a force that is performing a gauge in a gauge theory has to be massless. A gauge theory has to have a massless boson. Yeah, we could have massive boson. A helium atom stripped of its electrons is a boson, but it's not massless.
No, we're
it doesn't
talking
mediate a gauge
this
force.
theory of a new possible boson, which has several verifications, and it's being reviewed and all over the world right now. X17 is.
But what does it mediate? What force does it mediate?
It mediates the decay of the beryllium-8 was the first decay process that it was seen to mediate, but there are other configurations, there are other atomic configurations whose decay it seems to mediate. But it was initially discovered from beryllium-8 and then verified as the same mass of this possible boson in a possible bosonic process that is related to the decay of beryllium-8.
So what is it? How does it add to this conversation?
I hate to.
I'm just saying that we're talking about a massed boson.
No, a gauge force has to be mediated by a massless boson.
The weak
I've
force
heard
is
that too. I've
considered.
had to look at the
You need
proof,
another
The weak
explanation.
force is considered a gauge force, and it's it's not a scalar force like the Higgs, and it has mass particles.
Yeah, we have to look into that.
Yeah, but what gives it its mass? And this is the issue. And the thing is, Google this guy, John Moffat.
The Higgs
John
is
Moffat,
the Higgs is very generous. The Higgs is like in the process of conducting a potlatch with all the other particles to see who wins.
The Higgs would add.
Look at your mass. The Higgs gave you your mass, Michael.
You know, you explained it, Victor. My mass has to do with the nuclear forces between my nucleons.
That's
it has
right.
very little to do with the Higgs mass.
That's right. That's right.
The Higgs, basically, they came up with that theory to explain the masses of the W and Z bosons, which should be massless, but they know that they're not because they act.
Supposedly gives the mass to all the leptons, and it gives the mass to the quarks. The problem is that the 3 quarks in each nucleon are only are less than 3% of the total mass of the nucleon. So
Well,
that
my
is why
point,
the new
Victor,
theory is the strong interaction is
Victor,
responsible
my
for mass.
point is that the statistical data is invalid, that they base their claim in having discovered the Higgs boson. It's invalid. It's got to be valid to 5 sigma. It's only valid to 1.8 sigma. Maybe they upped it a little bit since
Well,
2015.
I agree that,
It's
scientists
all,
have
it
unlimited
Let
hasn't
Matthew
been
talk. Let
confirmed.
Matthew talk, Michael.
to
Let Matthew
justify
talk.
their behavior to world governments will always lead to perverse incentives.
Yeah, the whole thing is about funding.
At that
They
level.
didn't want to be closed down. The whole thing is about funding, and they got to show results.
Yeah.
Matthew,
And they were under a
I
lot
was
of
just
financial
seeing,
pressure
let
to
me,
show
let me say
results.
something to Matthew, Michael, personal thing. I just saw, I'm trying to become more aware of these things, even though we're on Zoom, but I was seeing little things in your facial expression and in your body language that indicated, Jesus Christ, I want to get the fuck out of here.
Well, yes, I was going to signal. I do have to go,
Okay.
but I was so enjoying,
No, it's Jesus fuck.
We
Jesus Christ, we want to get Victor the fuck out of here. That's what he was signaling. Now have a good week.
Yeah, I
guys.
gotta run. It's been real as always. Thank you
It's
guys
been
so
real.
much for coming out.
I apologize for Victor. What an inconsiderate. I apologize for Victor. I'm sorry.
We all do. Okay. All right. See you
Okay.
guys next
Ciao.
week. Yeah, we'll talk.
See you guys. Bye-bye.
Adios. Stop. Is that the longest one yet? Yeah, technically. Lol.